in the Department of Mathematics and Statistics at Queen's University, Canada. He received his Bachelor of Science degree from Bill Kent University in 2001 and MS and PhD degrees from the University of Illinois at Urbana-Champaign. And he was a postdoctoral researcher with Yale University before joining Queen's University in 2007. His research interests are far and wide. In particular, his works are on topics related to stochastic control theory, information theory, and probability. He is the co-author of some of the most popular textbooks, and he has also been a recipient of several top-tier awards, and he is also an editor of several journals in applied mathematics and control theory. Today, we will have the fortune of listening to his work titled Lift, Metrize, Quantize, Q-Learn, a general recipe for learning in stochastic control with general information structures. Over to you, Professor Sardar Iksel.
Good morning, everyone. Thank you for being here for the presentation. I'd like to first thank the organizers, Professor Toppe and Professor Bhatnagar. I very much would have loved to be there in person. I have been to India once, to Mumbai about 7 years ago, and I very much enjoyed my visit. Unfortunately, my obligations here, both academic and otherwise, dictated that I should not travel. So I apologize for not being there in person. And hopefully, at some other time, I can be there in person. So this talk is a very self-descriptive title. In particular, we will study stochastic control with general spaces and general information structures, and we'll try to give a general recipe on how to approach such problems. This has been a research team in our research group for some time. It builds on the work of some of my PhD students, former PhD students, Ali and Naji, and current PhD students, Emre and Omar, as well as my former postdoctoral fellow colleague, Somnath Pradhan. Somnath just recently completed his postdoctoral studies at Queen's, and now he's at the Indian Institute of Science and Education and Research, Bhopal. And he's been a fascinating, fantastic colleague, and I hope that you can get to meet with Somnath also. Now, what is the motivation? The motivation is that with stochastic control, often, especially in today's panorama, we deal with settings where what we receive, the information that we receive, comes from a very complex source. They are so complex that our traditional paradigms of modeling them as MDPs or PMDPs, it's very hard to justify. For example, we are connected through networks, through social media, through very different types of media where information is subjected to coding and decoding, and it is shaped by the bias of those sending us the information. It sometimes is impacted by artificial intelligence-based inputs or human input. So it really leads to a very complex source of systems that we are dealing with, and we still have to make decisions. And that is a very common phenomenon, and it's getting to be more and more complicated. And this is especially so in non-physical systems, for example, in social sciences, health sciences, right? These are also very common problems. And in such problems, we don't know much about the transition kernel. We don't know much about even a cost function. But what we have is, we have lots of data, and we try to make sense of the data. And the big umbrella question is, okay, how can I utilize the data to arrive at solutions which are optimal, near optimal, satisfactory in some sense? As I said, the main motivation is this third paragraph, because we are dealing with a very unknown, very complex environment. We don't know what we are dealing with. We don't know whether we have an MDP or PMDP. If there are multiple agents, we don't know who else is in the system. Right? So because there are many practical systems, setups where we work with data and we don't know the underlying model coming from data. Right? But nonetheless, often what we do is that we try to identify several key attributes, and then we use either physical reasoning or mathematical reasoning or data-driven reasoning to say that, okay, maybe some of the attributes are important in that they define the cost or reward, or they define some approximate Markovian evolution. For example, you can be a doctor, a patient coming to you, and then the patient can be a very complex individual, but you only look at a finite number of health data, and then you try to provide a therapy based on the limited data, right? So in a sense, you can think of it in that setup where you perceive some particular attributes and you try to view them as your state. The question is, if you run a learning algorithm by only using that state, which is not a truly Markovian state, but an approximate state, what can your algorithm give you? Does it converge? If it does converge, does it give you in some satisfactory performance? And this we'd like to view as stochastic control with non-Markovian data. And in particular, this has been both a classical subject, but also, especially in the past few years, a popular subject. So we had studied on this problem in the past few years, and Professor Borkar has done some, as always, foundational work on this subject. And there have been also some other studies by Van Rooij and others in the field. And earlier in 1990s, this problem was studied in part in a more limited context with the problems involving convergence. Now, so what I'll do is now I'll try to first give a general convergence theorem, and then we'll discuss some implications of this convergence theorem. So suppose that, as I mentioned, suppose that I have a stochastic process given by ST and UT. UT is will be our actions, and ST will be some general stochastic process, not necessarily Markovian. And as I mentioned, think of the application where, imagine I'm a doctor and I have a patient. The patient comes to see me, and I look at the vital readings of the patient. And based on the vital readings of the patient, I assign a therapy, and I try to see how the therapy evolves, how the well-being of the patient evolves, even though I well know that the patient is not a Markovian, does not have a Markovian evolution, at least as far as those limited readings are concerned. But nonetheless, I'm running a Q-learning algorithm in the following form. I'm pretending that my state is a Markovian state, even though it is really not. And I apply the standard Q-learning algorithm. Qt plus 1 SU is equal to 1 minus alpha TSU, QSU plus alpha TSU, CT plus B beta VT, where VT is the minimum over all states of the current Q function. And then I present some assumptions. The first assumption is that my learning rate is going to be what we call a linear learning rate. It is inversely proportional by the number of visits to the given pseudo state and action pairs. And I also require some ergodicity conditions, in the sense that my time average of the cost readings will converge to a fixed quantity, and my time average of the transition dynamics will converge to an effective average transition probability. Now, under these conditions, we have the following theorem. The Q-learning algorithm will converge to a fixed point, and the fixed point will correspond to the fixed point of a Markov decision process, where the cost function is the ergodic average of the time averages, and the P star is the ergodic average of the Markovian fitted data. Let's just remind what these were. Basically, C star is the time average. If you can look at this ratio. If you divide both sides by 1 over t, the lower side will give you the empirical occurrence of the set action pairs, and the upper side is going to give you the average value when the state and action pairs are visited. And likewise, you do the same thing for your transition kernel. So in a sense, your Q-learning algorithm is going to converge to a limit, and the limit is going to be the optimal Q function corresponding to an approximate Markovian process, for the Markovian process has the effective cost function C star and effective transition kernel P star. And a sufficient condition for the above to hold is that if your state process and the action process and the cost function, the cost readings satisfy the ergodic theorem in the sense that the time average converges to a stochastic average with probability 1. Now, so it's a very, I think, an insightful result in the sense that you do not have the Markovian setup, which is a traditional condition when you are dealing with a Q-learning algorithm, but you trade off the Markovianness with the ergodicity condition given here. And for graduate students, I just want to give a brief sketch of the arguments so that you see that the analysis is really not very involved. The idea is that you want to show that the Q functions, Qt will converge to some Q star. And to do this, if you have studied the proof of the very beautiful proof of cyclicless, Johnson cyclicless on Q-learning, you have to do some variation because in the proof of cyclicless, you are building on the martingale nature of the noise. But here, because of the fact that your error is no longer a martingale because you are dealing with a non-Markovian environment, you trade off the condition for Markovianness with the ergodic nature of the evolution. With that, what you do is you try to, using the linearity of the evolution, you write down the difference Qt minus Q star as the summation of delta, U, and V. You realize that the V term here only involves the evolution involving V star, P star, CT, C star. And we know that CT goes to C star, and V star of T will go to V star on average. Therefore, this is going to be your standard averaging dynamics, and it will go to 0. And then you are just left out with the terms involving delta and U. And with that, you just write down the terms involving delta and U. You obtain a contraction argument, and the result goes to 0. All this is to show for the graduate students in the audience that the analysis is really not involved, because sometimes even finding an accessible proof for the Q-learning algorithm, I do know by experience or by teaching that sometimes it may feel a bit daunting. But really, if you just sit down carefully and write down the arguments, it is just basic algebra. But the important message here is that you can trade off the martingale loss property by the ergodicity of the dynamics. Now, what is the implication for us then? So in a sense, you run your Q-learning algorithm, even though what you're dealing with is non-Markovian. As I mentioned, this has been an emerging research area in the field. And Professor Borkar, for example, has written several papers recently on the subject, which are quite foundational. Now, let's just see some implications of the discussion, because it's going to be a key tool for our analysis to come. Now, in a classical stochastic control problem, you have a state, you have action, and you have noise, right? As you know, if the noise is IID, then we know that any stochastic evolution system satisfies the conditional independence property with regard to the state and action, in the sense that the future is independent from the past if the current state and action are given to us. And in particular, we have this control Markov property. And of course, we also know that every system which satisfies equation 5 admits a stochastic realization of the form above. So in a sense, there's an equivalence relationship between this representation and this control Markovian evolution. And a process which satisfies condition 5 is called the control Markov chain. And if we have access to the state information, typically we call this the Markov decision process. And one talks about several optimization criteria. For the sake of clarity in this presentation, I'll mainly focus on the case where my criterion is a discounted cost criterion, but you can talk about other criteria also: average cost, finite horizon cost, costs up to an exit time, risk-sensitive cost criterion, sample path optimality, so on and so forth. There are many different criteria. And now for such a problem, though, when you go beyond the finite state action setup, you have to talk about some regularity properties. This is important not just for existence, but also it's important for approximations and for learning in the spirit of today's presentation. Then for regularity, we'll discuss a number of continuity properties. And the first one is what we call the Wick-Feller continuity. So a stochastic kernel, if you remember, what's our kernel here? Our kernel here is the conditional probability. Remember, given the current state and given the current action, the conditional probability of the next state is given by tau b given AB, meaning that the probability of the next state being in state B, being in set B, given that my current state is AT and my current action is BT. Okay, so this is my kernel, transition kernel. And we say that my transition kernel is weakly continuous if whenever x and un goes to xu, then my conditional probabilities will converge weakly. And as an example, if in the stochastic realization form, my evolution has this representation, xk plus 1 equals f of xk, uk, wk. And if for every wk realization, f is continuous in x and u, then this defines a stochastic kernel, which is weakly continuous. So as you see, it's a very natural condition. And in fact, it's going to be particularly important for today's presentation because weak continuity is often the most you can really hope for when you are dealing with an infinite dimensional dynamical system. For example, mean field models, for belief reduction of partially observable models, for like lifted models, or even deterministic models. So for example, if WK is not there, often weak continuity is the most that you can really hope for. A slightly more restrictive regularity is what I will call uniform Wasserstein regularity. In this case, you define the Wasserstein distance between the transition kernels when the state is x and u, or the state is y and u. In this case, the Wasserstein distance is has a modulus of continuity and a uniform one with respect to the difference between your current states under different realizations. And here's an example for this. If my evolution is given by this stochastic realization form, and if f is Lipschitz in x and u with Lipschitz constant alpha, then my transition kernel will be Wasserstein continuous. And in this case, this K2 is going to be exactly equal to the Lipschitz coefficient alpha. And a further regularity is what we call setwise continuity in actions. In this case, you say that my kernel is setwise continuous in actions for every fixed state x if whenever un goes to u, for every Borel set B, the conditional probability of that B converges to the conditional probability of that set B under action u. And here's an example which satisfies this property. For example, if your function f noise is additive, your function is continuous in u, and the noise has a density, and density is continuous. For example, if the noise is a Gaussian noise, then you satisfy the setwise continuity in actions. Now, why are these important? These are important because of the following. Corresponding to each of these criteria, you will be obtaining smoothness or regularity properties of your optimal solutions. Let us make this more precise. Suppose that you have a discounted cost criterion. You want to minimize the following infinite criterion where beta is some number between 0 and 1, your discount parameter. We want to find this minimization problem. And as we very well know, for example, if my cost is bounded, if you just define this discount cost optimality operator, then this defines a contraction. And when you apply value iteration, for example, as I'm sure many of you quite well know, as you update your dynamics, your value by this iteration, you obtain a contraction. And by Banach's fixed point theorem, you will have a fixed point. Now, under assumption S, your fixed point is going to be measurable bounded. Under the Wick-Feller regularity, your value function is going to be continuous. And under the Wasserstein regularity, your value function is going to be Lipschitz. So these three are important because now we'll be able to work with approximability. Right? So once again, the benefit of the different notions of regularity is that they give rise to the value functions, which are either just bounded measurable or continuous or Lipschitz. For average cost, the analysis is slightly more challenging, as is often the case. So in this case, you try to minimize the limit superior of the normalized sums. And in this case, there are typically three main approaches. One is what you call the contraction approach via relative value iteration. In this case, under certain conditions, you establish that these iterations are also a contraction iterations. Or another approach is to study the discounted cost problem and take the discount parameter to 1 and give a fixed state and look at the relative value of the discount value functions and try to extract a subsequence which will give rise to the following equation. So this equation is known as the average cost optimality equation. And finally, a third approach is what we call the linear programming approach, or the convex analytic method. And Professor Borkar was the pioneer in this, going beyond the finite setup of money to the standard model uncountable state space setting. In this case, you work with the properties of the ergodic invariant probability measures, their compactness and continuity properties. And the first two methods typically require some ergodicity conditions. For example, a minorization condition given in the following form. So for every state and action, there is a uniform lower bound, a sub-probability measure of going to any other Borel set in the state space. We call this a minorization condition. Or you need some Wasserstein regularity condition, where that regularity condition, the modulus of continuity, needs to be strictly less than 1. So if you are able to have these two conditions, then you can verify the average cost optimality equation. Okay. And I'd like to again note that because our goal will be to study the case where we'll work with infinite dimensions or we'll work with uncountable spaces, it's important to note that minorization is too much to ask for in general. So therefore, the Wasserstein regularity again becomes a key property that we will be looking for. Now, so far we discussed now some general existence discussion for average cost or the discount cost problems, and now our goal will be to try to first develop a theory for approximations for such MDPs with general spaces. Now, first, what we'll do is the following: we'll first establish optimality of finite models. And for finite models, we're going to first obtain a finite action model and then a finite state model. And then through these, we'll define a finite MDP. And then we'll show that the finite MDP is going to be near optimal in the sense that if I solve the finite MDP, and if I borrow a policy by solving the finite MDP, apply it to the true model, my policy is going to be near optimal. And then the nearness will be asymptotically vanishing, because the mismatch error will decay to 0 as my partition gets finer and finer. Okay. So this will be the first part. And again, we are setting the stage for learning, but first we have to do our approximation via planning. Now, because what we'll do is we'll partition our action space and state space. Okay. Now, the first part is the partition of the action space. So if my action set is compact, then I know that for every diameter, 1 over n, I can find a finite number of balls which will cover my action space. And in particular, we can state the following: under the weak feather continuity condition, for every epsilon, there's a large enough partition, there's a fine enough quantization such that the value that I obtain by applying a policy of the finite model applied to the true model is going to be within epsilon of the optimal policy. Okay. And the same applies for the average cost also. In particular, if the average cost optimality equation holds, and if I have weak continuity, once again, I can approximate my model as if my action set is finite. Okay. So basically, you can go from the compact action set to finite action set when you have continuity properties. Okay. Now, the more difficult part is to obtain a finite state model. finite state model is more involved because state manifests itself in both dynamics and also in the cost. And the construction is going to be slightly more challenging. Once again, suppose that my state space is first compact. We can generalize to the case where the state space is non-compact. Once again, you can, for every diameter 1 over m, you can find finitely many balls, which will cover the entire state space. And in particular, you can assign a nearest neighborhood quantizer, and you can assign each element into the nearest representative point in your finite set, which will be representing your original compact action space. In particular, you can define the pre-image of your quantizer as your bins, because this is a set of all states which are mapped to a particular element in your finitely many representative point set. And in particular, what you can do is now, you can, for each bin, assign a probability measure with full support on the bin, and through that full support, define an equivalence class, which will give rise to a cost function, which is going to be mapping a finite action space and finite state space. So then what we do is the following. So C of ZA is my original cost function. I'm taking the weighted integration over the bin, and I declare this to be my effective finite cost function. Now my state space is finite, my action space is finite, and likewise, this is my transition dynamics, conditional probability dynamics. I take the push forward of this to look at the probability of the state being in the next bin, and I take the average over all states inside my current bin. And I declare this to be my approximate finite transition kernel. So then what I've achieved is that I have a finite model for the cost, finite model for the transition kernel. So this allows me to construct a finite state, finite action MDP. And now then you can obtain several results. For example, under weak continuity, even when your state space is not compact, you can show that if I solve a finite MDP, again, by solving I mean this, I'm solving this problem. The problem with a finite state, finite state, finite action cost function, finite state, finite action transition kernel. I solve this, I apply it to the original problem. Then the result says that if I apply gamma hat, which is the optimal policy for the finite model, applied to the true model, then as my partition gets finer and finer, in this precise sense, basically if my partition gets finer and finer, then uniform over compact sets, my approximation error goes to 0. So then my policy, which I borrow from the finite model, is near optimal for the true model. Okay. And all I require is a weak continuity. And you can apply the same thing. If I will not go there, here I only say that I converge uniformly over compact sets, but there is no rate of convergence. You can also obtain a rate of convergence. In particular, the Wasserstein regularity that you have allows you to obtain a modulus of continuity for your approximation errors. In particular, if L bar is your maximum diameter in your quantizers, then your loss due to mismatch will have a uniform bound. And likewise, this applies also for the average cost problem also. Okay. So now there have been several studies on this. There are different variations, but here's two specific cases where you're able to obtain the results of this type. But my goal will be to try to make the connection with learning. So I'll give more general results later on in the context of learning. So the point is that the approximability by obtaining a finite MDP model, solving the finite MDP model, applying it to the true model, we are able to establish either asymptotic optimality or with optimality with a rate of convergence in terms of the granularity of your quantization. Now, let's go back to the first part of the presentation. Suppose now I have a general space MDP, and what I do is now I quantize my state, and I run Q-learning as if my quantized state is my Markovian state. So as you know, if you are given a Markov process and Markov chain, when you quantize the Markov chain, the quantized Markov chain is not a Markov chain because you lose information. In fact, you turn the problem into a partial observable model, because quantization is a measurement channel. You lose information. But nonetheless, in the spirit of the first part, suppose that I'm that doctor who is just wants to come up with a therapy. I just want to run my Q-learning algorithm. So I'm running Q-learning algorithm as if Q is the true state. But I well know that is not the true state. But building on this theorem earlier, if my learning rate is linear, again, I just take the histogram of the number of visits of the particular state and action realization. I take the inverse of it, run my Q-learning algorithm. Then you have the following. My Q-learning algorithm will converge to a fixed point. And the fixed point will be the fixed point corresponding to a Markovian model where the cost function is the average cost across each bin. But now the weighting average is not selected arbitrarily, but the weighting average is induced by the invariant measure induced by the exploration policy in my Q-learning algorithm. And likewise, my cost function, which I obtain as a result of this limit Q function, Q update algorithm, is the averaged transition evolution, where the averaging is done according to the invariant measure conditioned on each bin. So you see, it's exactly the same setup that we used to obtain a finite model, except that in the Q-learning algorithm, the weighting average, the weighting measure, is dictated to me by the invariant measure on the state process induced by the exploration policy. Okay. But nonetheless, I still have an approximation. That's the important part. So it becomes a special case of the approximation theory presented earlier, and in particular, the corollaries follow. So in particular, if you run the quantized Q-learning algorithm, as if your quantized state is Markovian, but as I said again, we know it's not, but if I pretend it to be as such, I still am able to obtain a uniform error bound. So gamma hat is what the Q-learning algorithm tells me my policy should be. I apply it to the true system, and my error is upper bound by this expression. And if my goal is just asymptotic optimality, remember I discussed earlier, if you only have one asymptotic optimality, then you will be converging uniform over compact sets. Then your approximation error will go to 0, in fact pointwise, but also uniformly over compact sets. Only if you have, by only asking for Wick-Feller continuity. And you can even discuss the case where when my space is non-compact and I still want a rate of convergence, you can have that too. You just need a slightly more involved argument, but nonetheless, what you can show is that you can obtain, if you have a total variation continuity now, you go slightly above Wasserstein, you go to total variation, you're also able to obtain also a modulus of continuity. Once again, let me just say it one more time. If I only have a compact space, a Wasserstein regularity, I have a uniform continuity as in terms of the diameter of my approximations. If I only want asymptotic optimality, I don't need anything else except for Wick continuity. Again, here in this case, my state space can be non-compact. And if I also want for the non-compact case a rate of convergence, then I need slightly stronger conditions. But nonetheless, under any of these setups, the resulting policy by applying the quantized Q-learning algorithm is going to be near optimal with explicit error bounds. Okay, and in fact, you can also give some sufficient conditions. For example, if you have a Lyapunov drift condition for your evolution, then you're able to control the moments of your state, and with that, you're able to obtain some further quantitative bounds. So the point is that you're able to study the compact case or non-compact case, and with a fairly accessible conditions for near optimality. So as I said, as a summary, if you do Wasserstein, then you're able to obtain a rate of convergence with uniform quantization. If you have Wick-Feller, then you are able to obtain asymptotic convergence, but with no rate of convergence. But if you have a slightly more regular kernel, then you're able to apply non-uniform quantization, and you're able to obtain also bounds for non-compact spaces with a rate of convergence. Okay. So the message here is that Wasserstein continuity and Wickler continuity are less restrictive, and they'll be very useful for our analysis to follow. As I mentioned, if you are dealing with the belief MDP reduction for PMDPs, which I'll be discussing shortly, if you're working with degenerate diffusion models, deterministic models, Mefield models, then we can only hope for weak continuity or Wasserstein continuity. But thanks to the theory we discussed by now, quantized Q-learning will work if you only have, even if you only have weak continuity. Now, and here's another implication of the discussion. So if I know that my quantized Q-learning algorithm will converge to an approximate, will converge to a fixed point, which is near optimal for an approximate model. And if my model is the model that I obtain by looking at the limiting distribution of the adjacent realizations of the state and actions in the following sense. So C star is basically the limit as the costs are realized for every given labels X and U, normalized by the frequency of visits of the state actions. And likewise, my effective transition kernel is my Markov fitted data, which is non-Markovian. Then this invites the following question. If I know that my Q function is going to converge to a fixed point equation for an approximate MDP, why not learn the MDP itself? And the MDP itself is the one that you obtain by fitting, as I mentioned, you fit the data to a Markov model. And the way you will do it is the following. You will count the number of adjacent visits of xk plus 1, xk, uk, and then divide by the number of state actions. This will be your Markov modeling of your non-Markovian system. And then you do the same thing for a cost function. Then this invites that, okay, maybe instead of running Q-learning, then you might as well learn the model, because they will give you the same results. And the benefit of this is that also empirical learning is intuitively more appealing in many ways, because the magic of stochastic approximation and Q-learning disappears. It just becomes a manifestation of the ergodic theorem. You just learn Markovian fitted data. Once again, just to say that I have a non-Markovian system, and I pretend it's Markovian. And if I pretend it's a Markovian, my P star is going to be the data that I obtain. And then the question becomes then, by the discussion we made earlier, my quantized Q-learning will converge to a limit where the limit is going to be the optimal control policy corresponding to this approximate model and this approximate cost function. And therefore, if I want as an alternative, I can just learn the model and solve the learned model to obtain my policy. And you can also go further. You can obtain a sample complexity analysis for this. In particular, you can show that as your partition goes to infinity and as your data goes to infinity, your mismatch loss goes to 0, the probability 1. And you can also obtain a sample complexity in the following sense. If you have some regularity conditions on your invariant measure, you can show that the policy obtained from empirical learning up to a finite n, finite sample n, you obtain an approximate model using only finite many data, then the expected mismatch loss can be bound in terms of the number of data that you have. So all I have to say is that instead of quantized Q-learning, you can also obtain empirical model learning, and they are both consistent, and sometimes the model learning gives you a more interpretable answers. Now, then using this general machinery, another comment or concern is the following. What if not every bin is visited? Because when you run a learning algorithm, often what you see is that, especially when your dimension is large, or if your state space does not allow you to explore every state and every action pair, then you have to refine your theory slightly. In particular, what you want is that you want to address two issues. One, the exploration policy that you use for your Q-learning algorithm may not have full support. Okay? In particular, the support of an invariant measure may exclude certain bins. And furthermore, and more critically, when you learn a control policy, and when you apply the control policy to a true system, you want to make sure that you never wander into the untrained territory. And some thinking then gives you the following. If the ergodic theorem holds in the sense that if your initialization is in the support of the invariant measure, then you can ensure that you will not leave the support. And furthermore, by portmanteau theorem argument, you can also ensure that when you apply the control policy that you have learned from the learning algorithm to a true system, if your initialization is either in the support of the invariant measure, or if your initialization is absolutely continuous with respect to the support of the invariant measure induced by your exploration policy, you will never leave the trained territory. Okay. So in a sense, you can make the theory work even if the support of the invariant measure does not cover the entire state space. And especially in many applications, if you do some simulations or experiments, you will see that this is more often the case. Now, the analysis also applies for the average cost case. As I said in today's presentation, the focus is mainly for the discounted cost case. For the average cost case, there are two techniques you can apply. One is that you can show that when the average cost of small-tail equation holds, if you set a discount parameter close to 1, the policy that you obtain for the discounted cost will be near optimal for the average cost problem. In fact, this is a generalization of a classical result by Blackwell for finite space setups, and it does apply also for the more general standard Borel setting. And furthermore, a near optimal policy for the discounted cost problem becomes near optimal also for the average cost problem. So this is one approach. Another approach is to directly work with the average cost setup. In this case, you can run a Q-learning algorithm tailored for the average cost setting. In fact, you can generalize the Q-learning algorithm of the classical one by Professor Borkar and Abunadi and Bertsekas, and you can generalize it, and the same machinery applies. Okay. But as I said, today's theme is going to be for the discounted cost case for the sake of clarity. Now, then as a reflection, we made the observation that Wick-Feldler regularity gives us asymptotic optimality with no rate of convergence, but also no need for compactness. Uniform Wasserstein regularity, it gives us rates of convergence, but it will require compactness. Then this provides a very general recipe as follows. Given a general problem, I will try to lift the problem to an MDP in a much larger space. We will metrize the space to make sure that our problem is going to be Wick-Feldler or Wasserstein regular. Then we will quantize the model, apply our Q-learning algorithm. And then we'll see that we can apply this machinery to PMDPs, multi-agent models, or control diffusions. Okay. So let me start with the case with the PMDPs. So suppose that I have a partial observable model. So in this case, I have an evolution of the state system as follows, and I have my measurements. So in this case, you can have a depiction like this. I have my state, I have my measurement, and I have my control policy. So in this case, the controller only has access to measurements. I don't see the state, I have the measurements. And I also know what I applied earlier. So in this setup, the controller does not see the states, the controller sees the measurements and the past actions. This setup is called a partially observable macro decision process. Now, a very important result in this domain is that you can lift the problem to an MDP, macro decision process, by replacing the state with the set of probability measures on the state. In particular, even though I don't know the state, I know what I think the measure on the state is. And in fact, the conditional probability measure, if you call this the ZT process or the filter process or the belief process, the belief process itself is a control Markov chain. And in particular, it has an evolution which we'll call the filtered kernel evolution. So in a sense, eta is the conditional probability of your next belief measure realization, given your current belief measure and your action. So this is a well-defined object, and it's a stochastic kernel mapping measures to measures now. Measures to measures on measures. And likewise, your cost function, your cost function is C. You take the expectation of the expectation, and then you see that the inner term can be written as the integral form as a function of your belief variable. Then this gives you an effective cost function. Therefore, you conclude that the lifted problem becomes an MDP with a much larger state space, the same action space, a different cost function, and the kernel given earlier. Therefore, in principle, partial observable macro decision process is just as difficult as a fully observable macro decision process, except that it lives in a much larger state space. But we can make the theory work by only verifying that eta satisfies our regularity conditions that I discussed earlier, either weak continuity or Wasserstein continuity or stepwise continuity. Now, this has been again a recent research problem, and Professor Feinberg and collaborators, they studied this problem, and they showed that in fact stepwise continuity for the kernel eta is too much to ask. And they showed that, for example, if your kernel is weakly continuous and measurement is total variation continuous, you're able to show that your kernel is weakly continuous. And then we were able to show that, in fact, you can have only one condition on the transition dynamics with no conditionals on the measurement kernel, and you can verify that your eta is weakly continuous. And again, as I mentioned, weak continuity is very important because it facilitates the existence and approximation and learning results that I discussed earlier. And in fact, you can also obtain a counterpart for Wasserstein regularity. And in this case, again, you need some further additional conditions, which are, for the finite case, in fact, they are applicable for every finite MDP. You can verify much less restrictive conditions. But I'm trying to give the most general conditions for this context. Then you are able to verify that under certain conditions, I realized that I spent too much time on the first part earlier. So I'm going to be going a bit faster. So what I want to say is that under certain conditions, you can verify that your eta process, remember eta is the kernel for your belief MDP. Then that eta process satisfies the Wasserstein regularity. Therefore, all the theory I discussed earlier is going to be applicable. Okay. Existence holds, approximation holds, learning holds. Therefore, for example, if you run your Q-learning algorithm for your belief MDP process, then you're able to show that when you run your Q-learning, obtain gamma hat from your Q-learning algorithm, apply to the true model, you have a convergence either under Wasserstein with uniform modulus of convergence, or only asymptotic convergence if you only have weak value continuity. And a further approach is the following, with the same spirit again. Now remember, in the partial observable setup, my admissible policies were those which you were using the entire past. And we made the observation that instead of using the entire past, I could only use, without any loss, my belief process, pi t. Now, then with my former student Ali, we said that, okay, what if instead of using pi t, what if we go back in time with n time stages, use the posterior or the predictor at time t minus n and the finite window. This information contains this information. Therefore, the optimal policy using this will not be any worse than the optimal policy here, which is optimal in any case. So therefore, this will give you an optimal policy also. And then we said, okay, what if we apply a quantization for this, where we quantize this posterior with a fixed entry, which effectively eliminates the measure here, and I only use my window size. So then this gives rise to a finite window model. And if you run out your Q-learning algorithm as if this finite window is your true state, then you run your Q-learning algorithm, you verify the conditions, and then you're able to show that your loss due to applying the finite window-based policy to the true system is upper bounded by this expression, where this expression is essentially the error between the conditional probability when you start from a wrong prior and the conditional probability when you start from the true prior. And this is what is known as a filter stability term. And you're able to show that if the filter stability term goes to 0 and goes to infinity, and for which we have specific conditions under different approaches, you're able to show that the policy that you obtain with applying Q-learning, as if your finite window is your true state, is going to be near optimal. Okay. Now we can apply the same machinery for what we call multi-agent systems. In a multi-agent system, sorry, I shouldn't say multi-agent, decentralized information structures. So in this case, imagine my system is as follows. There are L decision makers or L agents, and these agents impact the state, but each agent only has access to local information. So as you see, this is a generalization for the setups I discussed earlier. Now for this case, the challenge is that the information is not fully observable, is not partially observable, but it is asymmetric. Each agent has access to different information. So for example, as I discussed earlier, this is my state evolution. Actions are here. Each agent has access to some local measurements, and each agent can only use their local information. Now, suppose that we also allow the agents to have some information sharing and some local information. Then we are trying to minimize a cost function where each agent collectively is trying to minimize the same cost function. We call this a stochastic team, as opposed to a stochastic game. That's why I was a bit hesitant for using the term multi-agent, because typically for multi-agent systems, you implicitly assume that there's a game setup. Here we have a stochastic team setup. All the agents are trying to minimize the same cost function. Now, for solving this problem, again, just to give the spirit of the ideas, I'll focus on two information patterns. In one, each agent shares their information with one-step delay. In the other information structure, each agent is like the agents meet every Monday. They decide on what to do for the next week, and then they meet the next Monday. They share everything, and they meet the next Monday. They share everything, and the agents have to make their decisions during the between Mondays based on only their private information. So now what you can do is now, in fact, this has been studied in the literature, starting in the 70s, and Nayar, Majan, and Teneketsis gave a general recipe for such problems. And what you can do is now, you can, what you call you can lift the problem. And by lifting the problem, you define an equivalent state and equivalent action space. And in particular, your equivalent action space is going to be, in our setup, the set of maps from private information to actions. We endow these with what we call a Young topology. This will give us a metric structure on our space of actions. And then you're able to show that the policies that you obtain, so such a result was known for finite cases, and with my student Omar, we were able to show that we can generalize this by a measurability argument, meaning that policies which uses the original information structure, which are defined by policies which map the common information to the set of local maps, which is now endowed by the Young topology. You're able to define a lifted problem one more time. You're able to show that the lifted problem is a well-defined MDP. It's also Wick-Feller, and then you can apply your Q-learning algorithm. And you can do the same thing for the k-step information pattern. Once again, the information structure is going to be such that you share information periodically. Your state becomes the conditional probability. Again, I'll go a bit fast here. Your state becomes the conditional probability at the periodic times, and your actions become what each agent does in between the information sharing instances. These are function valued actions, but those function valued actions are given a metric structure with the Young topology, and then you're able to obtain a MDP in a lifted problem, and you can show that they are Wick-Feller. Then you can apply quantized Q-learning. Again, let me just give you the depiction for this. This is the original information structure. This is the lifted information structure. This is the information structure where we go back in time, we share a common finite window, and finally we restrict the true predictor with a fixed entry. Thereby, we eliminate it, and we effectively have a finite window. And finally, so we can apply the Q-learning algorithm for this problem. And the final application will be the diffusion process. Suppose that you have a diffusion problem. So B is your drift term, sigma is your diffusion term, the W is your Brownian motion. And I'm trying to control a system of this type. And for this types of problems, typically you need several conditions for the existence of a solution and also for existence of an optimal solution. In particular, suppose I have a discount cost criterion where I have a discount parameter, I take the integration as opposed to summation. Or you might have the average cost criterion or the ergodic cost criterion. Here you take the limit superior of the, you take the integration up to time t, and then you normalize by 1 over t. Now for these problems, as there's an excellent book by Professor Borkar and Ariel Postatis and Mirna Ghosh. Under certain conditions, you can ensure that there's a strong solution for your state process, and also an optimal solution for both the discounted cost and the average cost problem. For the average cost problem, typically you also need a Lyapunov condition, which will ensure that your invariant measures behave nicely in the sense that there's a compactness condition on the set of invariant probability measures. Then what you can do is now the following. You can quantize this problem by first discretizing the time. And then you can show that the solution for this time discretized problem becomes near optimal for the diffusion problem. Alternatively, you can obtain a discretization via what you call the Euler-Maruyama discretization. And you can show that the solution of this problem is going to be near optimal for the solution of the original problem. And then, now that you have a discrete time problem, you can apply the machinery I discussed earlier. In particular, we have two theorems. The first one is with Somnath-Pradhan. The value that you obtain by discretizing the diffusion is going to be near optimal. Making the control policy that you obtain by solving the time discretized problem applied to the true diffusion is going to be near optimal for both the discount cost problem and the average cost problem. And in the most recent work that we have been working with Professor Bayraktar and Ali and Somnath, you can run the quantized Q-learning I discussed earlier for both the discount cost problem and the average cost problem. Then it's going to be near optimal for the true diffusion. So, and finally, is my final slide. I will be able to finish on time. So what we did is we started with a general non-Markovian learning discussion. I tried to give some context, also some literature. Then we made the observation that under Wick-Feather property, quantized Q-learning goes to near optimality. And under Wasserstein regularity, we have a rate of convergence. And I tried to make the connection with model learning versus Q-learning. And then with that now, by only knowing that Wick-Feather regularity is what we all need for this machinery to work, then we say, okay, given a problem, I can lift the problem to a much larger space. I have to ensure that the lifted problem is an MDP, is a Wick-Feather MDP. Then I can run the machinery here by quantizing it using quantized Q-learning for Wick-Feather MDPs and run the Q-learning algorithm. We apply this to QMDPs in two ways, by quantizing the beliefs, the probability measures, or by using the finite window of measurements. Then we applied these to multi-agent systems. In this case, we obtained a centralized reduction, and the lifted MDP required an action space to be those with a topology under the Young topology. And finally, we applied this same machinery for diffusion problems. And in that case, we first discretized the time, and then we discretized the space. And then we were able to show that the policy that you obtain by quantized Q-learning is going to be near optimal for the true model. So with that, I am concluding my presentation. Thank you very much.
So thank you, Professor Yüksel, for this very information-packed discussion. So I now open the floor for questions. Please let me know if you have questions. Maybe I'll ask you one. So in this quantized Q-learning, I mean, there is, at a very high level, I saw that there is this convergence guarantee. Now, typically when you take Q-learning in the continuous action space and apply function approximation, right, the standard function approximation, you actually run into several issues. But I saw that in the quantized setting, at a very fundamental level, you at least have the convergence guarantees and so on and so forth. So my question to you is, if you want to take, let's say, the standard DQN type algorithm, right, and compare it with, let's say, Q-learning with quantized states and actions, would you like to give a comparison between the two? Like, where do you think one will work over the other?
So I think it's an excellent question. So often when you do the general function approximations or other methods, what the quantized Q-learning does is that because you are able to work with states and actions in isolation, you still have the contraction properties. So typically, when you do more general approximations, you lose the detachment because the geometry of the updates are violated with regard to a contraction map. One special case where this still holds is for the case where you have a linear structure, linear MDPs, but this is very restrictive. So in a sense, but to me, that's why the empirical model learning, I think, gives you a lot more insight. In a way, it says that if I will converge, what will I converge to, and what is it that I'm looking for? And Professor Shalmain has done some very interesting recent work on this subject. But yeah, I would say the answer to the question will be that with quantized Q-learning, you are able to keep the contraction property of the updates because you're able to isolate the states and actions from one another.
Okay. And in one of the slides, you talked about, ensuring whether every bin is selected or not in the quantized Q-learning case. So in practice, typically one makes use of some epsilon greedy behavior policy to ensure that every bin is chosen infinitely often, right? So wouldn't that idea work there as well?
Well, the state evolution, I cannot arbitrarily dictate which states I'm evolving. For example, think of a belief MDP. A belief MDP is an uncountable space valued MDP. And for example, if you only have finitely many, if you have measurements which have finite cardinality, that you can imagine, your beliefs are traveling very slowly, right? In fact, when you do an experiment, you will see that almost much larger portion of the state space will never be visited. So because you cannot guarantee that every state and action bin will be visited by just experimenting.
I see. Thank you. Are there any more questions? Okay. If not, let's thank Professor Sadda Yüksel once again. Thank you, Professor. Okay, so we now have a coffee break and we can return for the rest of the session. Thank you. Thank you, Professor Yüksel, once again. On day 3 of this reinforcement learning workshop. So I have the honor and privilege to introduce and welcome Professor Sridharan Devarajan. So I have also had the opportunity to work with Professor Sridhar. Okay, so if you remember, if you are part of the tutorial, I said that machine learning people think in a very different way, right? So I mean, if you want to say what machine learning people do, they solve problems, right? And when I worked with him, I realized that when there are very difficult challenges, he's able to come up with very elegant and efficient solutions to solve them. Okay, I think you will see this through this work as well. But on a formal level, his introduction stands as follows. So Professor Sridharan Devarajan received his bachelor's and master's from the Indian Institute of Technology, IIT Madras. He completed his PhD in neuroscience and subsequent postdoctoral training at the Stanford University School of Medicine. He joined IISc, where he is currently a faculty at the Center for Neuroscience since 2015 and an associate faculty at the Computer Science and Automation Department since 2017. His group studies the neural underpinnings of attention and decision making in the human brain, combining experimental and computational approaches, including neuroimaging, neurofeedback, and machine learning. His group also builds brain-inspired deep learning models for healthcare applications. So he has been, an excellent student in whatever he has done so far. His awards stand a testament to that. He has received a President of India Gold Medal at IIT Madras, the Stanford Graduate Fellowship, a SERB Early Career Award, a Wellcome Trust DBT India Alliance Fellowship, and a DST Savarna Jayanti Fellowship. He currently holds the Gaur Subraya Bhatt Chair Associate Professorship in the Digital Health at IISc. Today, he'll be speaking about harnessing attention in deep networks. Over to you, sir.
Thank you, Gugan, for the kind introduction. It's, I think, a little too kind. I hope, as they say, I can live up to the kind introduction in my talk. So thank you all for being here. Today, I was thinking, can you all hear me in the back, just to be sure? You can hear me? Okay, great. So today I thought I'd present some of our joint work that I've done with Professor Gugan on sequential attention-based sampling for histopathological analysis. And, before I delve into the details, I should acknowledge the team that did the hard work. So this is Tarun and Naman, two very talented MTech students who now passed out. Tarun was an AI student and Naman was a computer sciences MTech student. And of course, Professor Gugan was instrumental in bringing this project together. There's a reinforcement learning component in this project, and he was forever there supporting us, making sure that we met every week and actually made progress on the project. So it's really thanks to him that this paper saw the light of day. I should also acknowledge funding from various funding sources. And today I will be covering this sort of topic at a very high level. If you're interested in the details, the paper is already published and presented at NeurIPS last year. So you're welcome to take a look at it. You're also welcome to talk to any of us after the talk, and we'll be happy to clarify some details. Okay, so because a lot of the, I noticed that the symposium has like very theory-oriented talks, I thought I'll give a little bit of background on sort of deep learning models. Some of you may already have this, so I apologize if you already know all of this. So my talk will be focused largely on how neural networks can be trained to attend to different things, and we will talk about different modalities of attention, culminating in paying attention with reinforcement learning. But let's start out with a very simple deep convolutional neural network, right? So a neural network of this type, where, for instance, if the network wants to classify, the animal that you present, it's going to look for particular features of the animal, right? In this case, it's going to look for stripes, maybe. It's going to look for a particular kind of ear, a particular kind of tail, and it comes up with the conclusion that this is a zebra, right? So, but it has some level of, confidence that it could be a fox, maybe because the tail has a certain shape and so on, or maybe the ear has a certain shape. And also has some confidence that it is an elephant, but it's most confident that it's a zebra, right? Because these filters, the filters that look for stripes, are the ones that closely match the zebras, right? Now, the challenge with standard convolutional neural networks, in terms of how they pay attention, is that the weight that they afford to different parts of the input. So this could be input in terms of the parts, could be in terms of space, it could be in terms of features. But these weights are all frozen after training, right? So during evaluation, the model is not going to adjust these weights depending on the input, right? It's going to pay attention to things in a particular way, particular features in a particular way, right? And then it's going to make this judgment of what type of animal it is, right? But then there's a scenario where that kind of very inflexible weighting is not useful, right? So if, for example, you're trying to predict the upcoming word in a sentence, in a sequence, for instance, in general, and the sequence or a sentence is, she is eating a green apple, right? And so you've seen this word, she is, and then eating. Now this verb here is going to constrain the object that's going to follow, right? You've seen the subject, you've seen the verb, then it's quite likely that this thing is going to be some kind of food item, right? So in this case, it's a fruit, so it's an apple, right? So there's a very strong connection between the verb here and the object here. Similarly, if you hear the adjective, right, green, then there are only so many green objects in the world, right? So this connection between the adjective and the object is also quite strong, right? So these, if you pay attention to either the verb or the adjective, you can actually fairly well predict the object. But by paying attention to the verb, you can't easily predict the adjective. The eating and green are not very closely linked, right? So if a model learns to understand these types of dependencies, either in space or in time, then it can learn to flexibly pay attention and do better at predictions. So that's the idea that many sequence models, sequence prediction models and seek-to-seek models, etc., came up with. So in standard convolutional or fully connected layers, attention weights, the weights of the network are all very rigid, right? They are invariant to context. But in other types of networks, like global attention or local attention networks, the weight afforded to different parts of the input changes with the context, right? So if you are here, your prediction will be different. But if you've seen this verb also, your prediction of the object will be different because now the context has changed, right? So hopefully this idea is clear, and this is sort of the basis of a lot of your LLMs, right? So this attention mechanism is very strong and powerful in your LLMs, based on which it's making predictions. Can you do the same thing for vision models? Because I told you something about sequences. Can you do the same thing for vision models that are analyzing images? It turns out that you can. A very powerful class of models that many of you may be aware of, called vision transformers, represent not only local features like in convolutional networks, but also this type of contextual information, right? So basically what they're doing is they're dividing up the image into patches, providing position embedding for each of those patches. So just like your words have like a sequential order, the images have like a positional embedding, like which part of the image is this, am I analyzing right now? Is it the upper left? Is it the middle? And so on. And then they pass it into this type of attention network that ultimately produces some kind of classification decision. Now, the advantage of doing this with attention, obviously, is that rather than just looking at, for example, features like the eyes and the ears and, particular atomic features, you can look at them in conjunction, you can look at them in context, because there's another animal sitting here, maybe that context will inform you that this is also likely to be an animal and unlikely to be like a elephant or something like that, right? Because this is a domestic animal, so this is likely to be a domestic animal as well. So that context can maybe help you make your label prediction better, right? Okay, so it's just a very high level overview of attention. For those of you, again, who are already very familiar with all this, sorry for the repetition, but I think some of you may require this background before we move on to the rest of the talk. So what challenge are we addressing with these types of attention-based models? The challenge is histopathology. So histopathology, if you break down the word, histo refers to cells, and pathology is classifying diseases, right? So we're trying to classify diseases by looking at images at cellular level resolution. Typically when you're trying to, the clinician is trying to diagnose somebody for cancer, they do a biopsy, that is they extract some tissue from the patient. That tissue is sectioned, it is stained, and then mounted on a glass slip like this, right? Like a glass slide like this. Then the histopathologist is a very trained individual, right? Years, decades of training. What they do is they look through the objectives of a microscope. Many of you may remember this from high school. So those of you who took biology may remember that each objective has a different magnification, right? So you start by looking at the lowest magnification. Then the histopathologist decides, where should I go in the slide? Which part of the slide is likely to contain the tumorous cells? They move there, switch the magnification, higher magnification. And then they have to keep doing this because only at the highest magnification where the cellular level details are visible, right? Because at this level you can't make out anything, right? So at the cellular level resolution is where they can actually make a genuine decision. They have to be very careful because neither can you have random false positives. You can't say that somebody has a tumor when they don't have one, nor can you afford a miss, right? That can also be very expensive because you can't miss the fact that there are tumor cells. But this is a very slow and painstaking process because you have to look through the slides very carefully at high resolution, taking very informed guesses. And I've spoken with histopathologists who do this, and it turns out that they very often follow rules of thumb because it's impossible to look at every part of the slide at high resolution, right? So they have to sacrifice, some level of accuracy for some time. So they follow a certain kind of rule of thumb, like scanning with like a Z and so on and so forth. And these are all like very ad hoc recipes, right? So sometimes it may lead to like false results, etc. Right? So what can we do to help? So as computational scientists, as computer vision scientists, what we can do is we can take the slide and digitize it and convert it to a whole slide image, right? So just to give you an example of how this looks like. So this is an example of the slide that is digitized, but at different levels of magnification, right? So this is some, representative 1x, 10x, 40x. This is from a public data set called Chameleon 16, it's a benchmark data set. And what you will see here is that at the 1x magnification, there are tumor cells here, but you can't see them. Only when I zoom into 40x, the full high-level magnification, can you actually see that there are healthy cells here and there are tumor cells here. And the clinician, the histopathologist, has taken incredible pains to mark out this boundary between the healthy cells and the tumor cells. Now, obviously, for the histopathologist to do this for every slide is going to take a lot of effort. So 9 out of 10 times, we will not have this detailed annotations or boundaries. The histopathologist will look at the slide and then they will simply say, yeah, there is a tumor here somewhere, right? And then they just leave it at that. This I've only shown you so that you can get a sense of the boundary between these two cell types, right? Okay, so now you might wonder, okay, so why can I not take the whole slide image that is digitized at high resolution and just feed it into a deep learning model, right? So that's a possibility. But it turns out that that's not that easy. Maybe if you're in industry and you have access to like very powerful GPUs, you could. But for most of us academics who can afford only like mid-level GPUs, these high-resolution WSIs are very, very large images. They will not. They're gigapixel size. They will not fit into a single GPU memory. Typical GPUs these days have whatever 24, 48 GB RAM, but the things again that academics can afford. So these are things that will not fit this type of slide. Even a single slide may not fit on a GPU. Forget doing batching and all that, right? The other problem is that you can say, well, why should I not then just take the image patch by patch and feed it? And then I'll make some classification decision, right? So why should I feed the whole image? But it turns out that that's computationally expensive because you have to go through every little patch in the image and then make a classification. So that's computationally expensive. It is also inefficient because diagnostic regions in the image are sparse. What that means is, if I showed you a large WSI, the place where the tumor cells are there is only a very small fraction of the entire WSI. So I could be going over like all the top part of the WSI for like half an hour and end up with nothing, whereas the tumor cell is somewhere hidden in the bottom, right? So what I need is a way to intelligently sample only the most informative patches in the same way that a histopathologist does, right? The model needs to develop an intuition for where to go. Without looking at all the entire slide in high resolution, even at low resolution, the model needs to develop that sort of intuition. That will reduce your inference time and computational load. But you have to do all this without sacrificing classification performance. Again, like having a false negatives is a no-no, and absolutely false positives is also a no, right? So you can't either miss a cancer that is there, nor can you say that there is a cancer when there is not one, right? So this is all exactly how a histopathologist would do it. So can you come up, can we come up with a scheme to mimic what the histopathologist does? Just before introducing what are the existing state-of-the-art methods for this solving this problem, I'll give you a little bit of background and notation. This is, for those of you who are interested in, looking at the details of the model, this will be helpful. So basically, if you have a low-resolution whole slide image, this is what it looks like. And what we do as a pre-processing step is we remove all the background, because all the background material is irrelevant. That's on the slide that does not contain tissue, right? So we remove all of that. and then divide it into a bunch of non-overlapping patches. Now, this is the WSI representation at low resolution. We pass it through a feature extractor, which is a pre-trained VIT. If you're interested, I'll go into the details of it, but this is a VIT that is trained specifically for extracting features from cancer images, right? And this produces a n cross d dimensional representation for the entire slide. Now, capital N is the number of low resolution patches, and small d is the dimensionality of the vector output by the VIT for every one of the low resolution patches, right? So is this notation clear? But the story doesn't stop there, because we can't make a classification decision with this resolution, right? This is the challenge. So then what happens is you have to zoom in, right? So that every low resolution patch corresponds to a bunch of high resolution patches. And let us assume that there are small k high resolution patches for every low resolution patch. So if you pass those through a VIT, you will get a feature representation that is n cross k cross d, right? Because there are n low resolution patches, k high resolution for every low resolution. So n cross k total high resolution patches, and every one has a d-dimensional representation. Okay, so hopefully this notation is clear, right? So now let's delve into some previous work based on this notation, what people have done to solve this problem before, which will be relevant for, because we build upon previous work, right? So it's important to cover that. So as a quick show of hands on how much time I should spend on this, how many of you have heard of multiple instance learning? Okay, only a couple. So maybe let's spend some, little bit of time on this. So normally, if you train a classifier, an SVM, and so on, you have what's called a label that's associated with each instance. So imagine these are all images of cats and these are all images of dogs, right? So for every image of a cat or a dog, you will have some label associated with it. And then your classifier will learn to draw some boundary between the categories, and will say, okay, this is a cat, that's a dog at inference time. In multiple instance learning, things are slightly different. The entire bag of many instances receives a label. So here what you will see is that there's a lot of collections of instances here. Instances means like, images, for instance, in this case, right? Or patches, right? So all of these patches together get one label. Now, what is the rule? If you look carefully, you will notice that only if all the instances are negative does the bag get a negative label. Even if one instance is positive, the bag gets a positive label, right? So this is an example of multiple instance learning where you're not labeling things at the instance level, you're labeling things at the bag level, and then you're trying to draw a classification boundary. Obviously, this will be much less precise than what you can do with single instance learning because you don't have instance level labels. But let's make this concrete by asking where this is useful for us. It turns out that this MIL is particularly useful for whole slide image classification. Why? Because, like I already told you, if I try to create labels for every single patch, then the histopathologist is going to have a long day, right? They're going to have to sit and draw these boundaries across the patches in every slide. Since I don't have that information, all the histopathologist is saying is this WSI has a tumor somewhere, right? Now then what I can do is I take all the patches in that WSI, put them into a bag and say that slide is a tumor slide, right? I completely label that entire bag as a tumor bag, right? Whereas if the histopathologist just looked carefully at the slide and there is no patch that they can identify that has a tumor cell, then they are going to say all negative, right? So everything is clean. That means I'm going to give it a negative label, right? So now I'm labeling things at the whole slide level with the understanding that many instances in that slide could still be negative, but even if there's one or few positive instances where there's some small fraction of tumor cells, I'm going to give that entire slide a label associated with a tumor, right? This is where multiple instance learning comes in handy. So to cut a long story short, there have been many groups in the past that have worked with this type of MIL model, and some of the more recent work looks at attention-based multiple instance learning, right? So I already introduced attention in the first couple of slides. So basically what these authors do, for instance, is they take the whole slide image and divide it up into this n different patches, and each patch, low resolution patch has k high resolution patches. they create a d-dimensional representation for each of these, and then do multiple instance learning, but with attention weights. So rather than directly taking this and throwing it into a classifier, into an MLP type model, what they do is they do a weighted aggregation based on learning an attention weight for every single one of these patches. Now, what do the attention weights tell you? The attention weights tell you in this context, right, in this type of slide, how much attention should I be paying to each one of these patches. So if it's a tumor patch, in an ideal case, you would pay more attention. And if it's not a tumor patch, you would pay less attention, right? Because that's not particularly useful for classifying it as a tumor, right? And so then you do a weighted aggregation, pass it through a classifier, and then you obtain your classification label, right? This is attention-based multiple instance learning. Now, what are the disadvantages? I mean, this is some math associated with how the attention weights are calculated. We're going to skip that. Now, what is the disadvantage associated with this type of attention-based multiple instance learning? It is time intensive and inefficient because all the patches are processed at high resolution. You have to look at all the patches at high resolution to decide how much attention weight to give each of them, right? So this is inefficient. This is what we want to avoid, right? Because that's going to, A, be challenging on the GPU, or be computationally intensive if you decide to go through everything serially, right? Now, the actual model that we're going to build upon is called attention challenging multiple instance learning. It's slightly more complex than ABMIL, but not that much. Basically, all it's doing is it's learning multiple different attention heads. So what ABMIL does is it learns to pay attention to one particular kind of features, right? Because it has only one attention head. It learns to pay attention to certain kinds of features based on this attention network that it has been trained on. Now, whereas this ACMIL, what it does is it learns multiple different attention heads. Now, each of these attention heads is based on a loss function, is forced to be as different from each other as possible. So essentially what we are saying is, if I pay attention to one kind of feature, I can tell fairly well whether there's a tumor or not. But what if certain tumors did not obey that rule, right? In my data set, there could be tumors that have different kinds of features. Then how do I identify them? By learning different kinds of attention features, right? So learning to pay attention to different kinds of features. Now, once you pay attention to one kind, another kind, and so on, you aggregate all of their decisions and then make a final decision. So even if one of those features is there in your slide, you say, okay, this is likely to be a tumor slide, right? And then there's certain, again, niceties associated with the loss function, which we will skip. But the basic idea here, the L3 is the most important, where these WAWJs, that is the attention weights associated with the different heads, are forced to be as different as possible, right? So it's trying to minimize this similarity, right, between every pair of WIs and WJs. So the model starts to look for very different features when identifying tumors. Okay, but what is the disadvantage with this? It turns out that, again, because you're looking through all the patches, it's just building upon ABML, right? So looking at all the patches at high resolution, it ends up being time intensive and inefficient. Okay, so this is one audience for whom I don't have to do this intro to deep reinforcement learning. Because I think many of you probably here because you're interested in reinforcement learning. So I'm not going to go into details here. I'm just going to say that reinforcement learning, especially for neuroscientists like me, is particularly attractive because it mimics how humans learn by trial and error, right? So when an agent interacts with very unstructured environments and receives like sparse rewards and all that, that mimics very much how animals and of course humans also learn. Very often there's no instruction signal associated with every sample and so on. So this is quite attractive for me, as a neuroscientist also to get into, but it turns out it's also useful for our problem. I'll only leave with saying that Jan LeCun in Europe's had this slide where he said if intelligence is a cake, the bulk of the cake is unsupervised learning, the icing is supervised learning, and the cherry on the cake is reinforcement learning. And I guess the reason why he said this is because there's very little information that you give to a reinforcement learning model to help it learn compared to the amount of information that's available for unsupervised and supervised learning. But I take it to mean that it's sort of the pinnacle of all learning, right? Because the cherry on the cake is right at the top of the cake. So, anyway, so, but this concept of combining reinforcement learning with deep learning has met with a lot of success. Probably some previous speakers also covered this. And as neuroscientists, I was particularly excited when we saw this paper come out like I think about 10 years ago. Date might be wrong. So it's about 10 years ago. This is in Nature called Human Level Control through Deep Reinforcement Learning. This is a paper by DeepMind where they introduced a deep Q model that could just take as input frames of an Atari game, process it through a convolutional network, a fairly standard convolutional network, and through Q learning, learn to play the game, right? There's a finite action space, and it's learning to do what to do in every frame, move up, move right, shoot, whatever, and so on. And it's learning to do this purely with reinforcement learning. No explicit instruction about this is your enemy, this is your bullet, whatever, right? No such thing. It's just being fed the image as it is, pixel level information. And the thing that actually struck, at least myself in particular, is that it started to develop strategies. The deep Q agent started to develop strategies that are very human-like. So again, how many of you are familiar with this game? So usually, people don't know these games, so it makes me a bit sad that I'm old, but how many of you know this game? Okay, good, all right. This is a game where you have a paddle that's moving around, and then you bounce a ball off and you hit the bricks, right? And it keeps breaking the bricks. Now, one very human strategy that people develop is to create a tunnel, right? There's a strategy is called tunneling. You create a tunnel and then let the ball sort of bounce off to the top part, and then it'll destroy a lot of bricks even without you having to intercept it when it comes down. Now, this type of strategy for many different games, these types of very human-like strategies, the RL agent was able to develop, and they were able to show that there were these, very interesting parallels with human performance, right? So this was quite exciting for us, but I guess there's still a lot of mysteries about how this works, whether this works in all cases, and so on. But just discounting that for a moment, it was quite interesting. And the place where it actually got to a real genuine amazement was when it started beating the master at this grandmaster, like a chess grandmaster, at this game called Go. I don't know enough about Go, but what I've heard is that this game is so complex that unlike in chess, where typically people can say that I'm, this particular strategy and I'm going to move this pawn and in 6 moves mate and so on, here they play by intuition. So they don't even know why they're making a move, and after some 16 moves, they will suddenly realize this is the reason why I made that move so many moves ago, and I started learning to beat them at this game called Go. So this was again, created a lot of splash among the folks who were, because we are interested in cognitive neuroscience, and beating a human master at this type of game was very exciting. So the question that we asked, which is relevant to this particular study, is can we use this type of deep RL agent for scanning whole slide images and for playing this type of game, and instead of going through all the patches in the WSI, can we use the RL agents somehow to intelligently sample the slide, right? So what's the RL agent doing? It's quite simple. We take the WSI, divide it up into patches, and every patch has a state vector associated with it. That is ST, right? Now the RL agent's job is simple. It just decides which one patch should I visit and sample at high resolution. So should I go here and sample this, or should I go here and sample this at this time step, right? And this particular time step of this episode, where should I go? Once it goes there, that patch is zoomed in, and when it's zoomed in, you get a feature representation associated with this particular patch. And then this is a bit of a critical part. I won't go into the details, except to say that there's another network here that is going to now, based on this low resolution representation and the high resolution representation of the limited patch that this agent has seen, it is going to take a guess of the high resolution representation of the rest of the image, right? Now, once it makes this guess, of course, initially the guess will be poor. over time, hopefully the guess will become better and better as it visits more patches at high resolution. Then it's going to go back, select another patch, and then go back, select another patch, and so on and on until it's ready to make a classification decision, right? Now, obviously, if this happened n times, capital N times, then we are no better than standard models because we're visiting all the n patches at high resolution. So if this needs to be an efficient algorithm, the only way we can claim that efficiency is if, without compromising classification accuracy, we can visit only a small fraction of the n patches. It's typically 10% or 20%, as you will see later. Only a fraction of the n patches you visit and then make the classification decision, right? And then, yeah, the RL agent learns through this type of reward. So this is a model called R-Logist, standing for reinforcement learning based histopathologist, that was suggested by this colleague, group Zhao and colleagues. Just to give you a visualization of how this, the intuition for, what I just said. Let's just see if this plays, yeah, okay. So it's basically like the RL agent is visiting. These color patches are the ones that are visited by the RL agent. But basically what happens is, as it visits, it gets a clearer and clearer picture of the entire slide, right? Even though it hasn't visited, for instance, this patch. It has never visited this patch, but its guess of what this patch would look like keeps improving even as it visits other patches. Now, how it is not magic, it happens because there are spatial correlations among the patches, right? There are things that you can exploit about the structure of the image. Just by visiting certain patches, you can have a good estimate of what the other patches would look like. And if you do that, then essentially, and if you have a good estimate, then you can make a classification decision. This is the basic idea, right? And then ultimately it zeroes in on the tumor patch, and then you've nailed the classification decision, right? So just an intuition for what's going on, right? So what is the disadvantage with previous models? It turns out that there is a certain performance bottleneck because their feature extraction is generic. There are certain reasons why their RL agent training was unstable because they're trying to train too many things at once. They provided only a sparse terminal reward, so only at the end of each episode did they provide a reward. And the biggest challenge, it turns out that this was developed by a company and most of the code is proprietary. So you can, we couldn't actually take that code and recreate what they had done. We had to write everything from scratch. And so essentially, this turned out to be also the performance is not, anywhere close to the state of the art, right? So how do we improve this model? So we have a feature extraction that is tailored for cancer images. We have stabilized the training of the RL agent using certain tricks, which I'll go into in the next, 2-3 slides. We provide frequent and interim rewards. That is, at the end of every step, the agent makes a prediction. It doesn't wait to make a prediction at the end of the episode. It only makes a prediction at the end of every step in the episode, right? And then, of course, we've open sourced our code, and you're welcome to look at it, if you're interested. Okay, so how much time do I have? 20 minutes, okay. Okay, so now this gives me a little bit of time to go into some of the details of this work. So this is where the notation that I introduced before will come in handy, right? So what is special about the way we are extracting features that is different from the way the previous model was extracting features? It turns out that we have two different attention networks, right? So the first attention network takes your n cross k cross d representation, and for every high resolution representation, it learns a certain attention weight associated with it, and that brings you down to an n cross d representation, right? So basically now every low resolution patch which was visited at high resolution has been brought down to a d-dimensional representation. So your slide level representation is no longer n cross k cross d. By using attention weights and collapsing across the k dimension, we have brought the representation down to n cross d. So every patch now has just a d-dimensional vector representation. The second attention weight, so this is hierarchical, so the next level of attention weight, what it does is it learns n different attention weights across the n low resolution patches. That information is then fed to a classifier. It's brought down to, of course, a d-dimensional representation. That is fed to a classifier to make a prediction, right? So this is the classifier. Now, why is this advantageous over conventional models like ABMIL, ACMIL, and so on? Remember that in those models, you had to learn n cross k attention weights, right? Because you are learning an attention weight for every high resolution patch. Here, you are learning attention weights for every k attention weights for every high resolution patch. And then you're breaking it down into two steps. In the second step, you learn capital N attention weights for every low resolution patch. So effectively broken down the problem by sort of attacking it hierarchically, right? So this, there it is n times k, here it is n plus k, right? So that's the, makes the analysis and the number of weights that you need to learn simpler, lesser, and less complex. So this idea is efficient learning of representations while without compromising classification performance. Okay. So that is one innovation. The other innovation is we have something called a targeted state updater. So what does this mean? So when the RL agent visits different patches in the slide, it is not going to update the entire slide at high resolution like I showed you in the GIF, right? I just showed you a graphic of how that works, but it's not going to do that. What it is instead going to do is something a little bit more efficient. It's going to look at all the patches that are similar to the current patch in terms of a certain metric, here cosine similarity, and then it is only going to selectively update those patches. It's not going to update all the patches. So this is a targeted state update mechanism, right? And there's a certain way by which this targeted state update mechanism learns. We'll ignore the details for the moment. But the essential idea here is that this state update mechanism is not global. It exploits similarity between patches for updating their representations. So you're again updating more efficiently. Instead of going across the entire slide and updating every patch, you're only updating a subset of the patches. The components of the model are like this, and this is, I'll also introduce the third innovation in this. So here, basically, you have all the different patches in the, that are accessible to the RL agent. Based on the policy network, the RL agent decides which patch to visit. Then, based on the targeted state update, you decide to update patches corresponding to, the similarity with the visited patch. You zoom into a particular patch, do the state update. The state gets updated based on the high resolution information of the visited patch and the low resolution information of the older patches. Then you make a classification decision at every step, and the RL agent learns through this binary cross entropy loss associated with basically the label loss, right? So at every step, based on the state vector, this ST plus 1 of I, the RL agent is making a classification decision. Is this a tumor? Is this not a tumor? Only during training, right? Not during evaluation. Only during training, the RL agent is learning through this loss. So this is interim rewards, makes the training a lot more stable. Again, this is the Sasha model in all its gory detail. So if you're interested, you can go into the paper and look at this. Again, happy to talk to you about this if you're interested. Okay, so now how do we do vis-a-vis previous models and methods? Obviously, as any conference paper would have, we have a large table in the paper with like some dozen different models and comparisons. But here I'm only presenting like, one or two, just to give you a high level view of how well we do compared to at least our closest competitor, right? So that closest competitor is R-Logist. And what you're seeing here, these two big groups of rows, this is one benchmark data set, Chameleon 16. This is a breast cancer data set. And this TCGA is a lung cancer data set, right? So these two groups of rows correspond to the two data sets. Each column is one method, right? So this first column is R-Logist, then Sasha is our method, and so on. Point 1 and point 2 here refer to the fraction of patches that were visited, right? So point 1 means 10% of all the patches were visited. Point 2 means 20% of all the patches were visited. This method here, HAFED, is the ceiling, where all the patches are visited. So ideally, any sort of subsampling strategy cannot do better than the ceiling performance, right? So if you're doing, ceiling is the maximum you can do. You visit all the patches at high resolution, this is the best you can do, right? These are the sort of the best numbers. So you can already see that in terms of different metrics, accuracy, AURC, F1 score, etc., we are doing substantially better than Sasha. Here we are, you have NAs in certain columns because their paper did not report certain numbers. And we have no way of replicating their code because the code is not shared, right? So we are reporting the numbers as if from their paper. And these numbers are what we have generated from our model. And this for 10% of patches visited, we are doing well. For 20% of patches visited, we are doing better. But what is particularly interesting is the comparison between this penultimate column and the last column. Why? Because this is the number that you want to hit if you're doing, really well, right? But even with sampling 20% of the patches, we are close to these numbers, right? We are not that far from these numbers, which means that we don't need to sample that many patches, to really do this well. We only need to sample a small fraction of the patches, and we do as well as if we had sampled 100% of the patches. Now we've done other sorts of ablation studies where we visited 20% of the patches at random, right? Where the policy network is just turned off and we just visit 20% of the patches at random, and we do substantially worse than this. Which means that there is something intelligent that the RL agent has learned in terms of sampling, which allows us to achieve performance that's comparable to the ceiling performance, right? Okay. So there's a few other advantages. Because again, we're visiting only 10 or 20% of the patches, we have substantial speed up over state of the art. So these are other methods. I didn't have time to introduce them. This is called DTFD, and ACMIL is the one I spoke about in the beginning. So these are methods that again sample the entire slide at high resolution. And here, this is on the y-axis is inference time, and you can see that our methods perform much faster. Again, because we're only sampling a fraction of the images. This is at inference time, right? Now there's one more, aspect where we do well, which is compressibility. Now, why do we care about compressibility? It turns out that if, when we had this discussion with some clinicians in a cancer hospital in Uttar Pradesh, they mentioned that they have lots of these WSI images, lots of WSI slides. And they don't know what to do with the WSI slides because once they digitize them, they don't have the space to store them. They don't have the resources to store them. They don't have the resources to keep them intact for a long time. They're fine with storing the slides because for the patient, you have to do the sectioning and store the slides. But to digitize and keep them, they don't have the infrastructure. So then they asked, is it possible, right, to get a more efficient representation of this slide image that you can store and keep archived for a fraction of the cost. And what this graph is telling you is that you can indeed do that. There are, other models also have very efficient representations, but we are doing even better than them, again, because we are only visiting a small fraction of the patches, right? Now, what is the caveat here? The caveat here, again, for those of you who are very familiar with computer vision models, is that once you've compressed, it is not lossless compression. You will never be able to go back to the exact original whole slide image by taking this feature vector and then trying to reconstruct the slide. That's not going to happen. You can train models to do things like this, generative models to do, but you've lost information, right? But what is useful is the diagnostic information is still preserved in the feature vectors, right? So things that they would need, if they put our decoder at the end of it, took these features and passed it through a decoder, they will still have diagnostic information about whether there was a tumor or not. And also, I will show you in the next slide where the tumor was in the slide, right? So, this is a bit of a, we have to, when we propose this solution, we have to be careful when proposing it to clinicians because they should not think that, oh, if we just have this compressed vector, then tomorrow I can just expand it into the whole slide image. They can't do that, right? Only the diagnostic information will be preserved. Right? So then the other aspect is reliability. So especially when you're working with clinicians, the question that they will ask is, how do I know that your model is not following some shortcut to find the answer? Many of you may know that deep learning models are very prone to making strange associations, right? So for instance, the model can predict that there's an elephant in the image, not by looking at the features of the elephant, but by looking at the background grass and so on, right? So that type of association, if you have to avoid, then we have to show them on what basis the model is making the diagnosis, right? So for that, what we do, and in this type of RL model is very easy because you just tell them where the model sampled in the whole slide image. Did it visit the tumor patches or did it just go randomly sample some corner of the slide, right? So if you look at this, representation and the boxes are the places where the model has visited, the fraction of tumor patches that the model visited are substantially greater compared to a model that was just sampling randomly, right? So it not only visits a greater proportion of tumor patches, but the fraction of tumors in the patches that it has visited versus not visited is greater, right? So that automatically means that the clinician can now use this model, right? So even if they are not willing to trust the judgment of the model, they can still go and look at the places that the model has visited and then zoom in and see is there a cancer cell there or not. It just aids them, right? It assists them. The other thing that clinicians need is something called model confidence. That is, they need to know how confidently the model is making a prediction of whether there's a tumor or not. And for this, there's something called the expected calibration error. There's a metric that allows you to tell, how confidently the model is making a decision. And we find that our ECE for this particular HEFED model is actually very low, which is the full high resolution model. But for the 10% and 20% patch visit Sasha models also, it's not bad. For the 20% model, it's actually much lower than even state of the art. So it suggests that the model is fairly confident, correctly calibrated when it is making correct decisions. When it is making incorrect decisions, it is a little bit less confident, right? Now, if you convey this confidence information to clinicians, and if the model is again well calibrated, clinicians can be a little bit more, they can trust the output of the model more, right? So if the model is making very confident incorrect decisions, then that becomes a problem. So this type of calibration is another aspect that's important for clinicians. Okay, so let me just conclude. So this, the model that we propose, Sasha, is a novel combination of multiple instance learning with deep reinforcement learning, which we've applied to cancer histopathology. We've shown advantages in terms of efficiency, in terms of speed, and potentially storage savings also. Reliability in terms of sampling the tumor patches more often than the non-tumor patches and with calibrated confidence. And even if, again, like I mentioned, the histopathologists are not willing to sort of give up their job, it can assist them by saying that, look, these are the places where I think the tumor is there. Now you make the decision, right? You go sample those places. You zoom in. You don't have to raster scan the whole slide. Just go to those places, sample them, and make the decision for yourself. So for their inspection, the model can provide like an assistive technology. Okay. So where are we going? I mean, you can imagine there are many different extensions. There's the fact that you're doing low compute and sparse sampling, right? You're not sampling all the parts of the slide, is particularly advantageous for real-time applications. It's actually an extension that we are currently working on with Professor Gugan. So the particular problem that we are working on is epilepsy seizure detection, because many of you may know that epilepsies are temporal anomalies, right? Just like the cancer cells are spatial anomalies, epilepsy seizures are temporal anomalies in that there's like a very non-standard distribution of the neural electric potentials that happen when a seizure onsets. Even before a seizure onsets, there are certain signatures of that. So can you predict an epilepsy seizure based on this type of sparse sampling? Because the EEG data that is coming out of the recordings is all coming out from many channels sampled at high resolution. But by sampling only a small fraction of the channels and maybe even at low resolution, can you predict seizures? And then there are other challenges, interesting challenges on MRI-based dementia classification. Can you look into abnormalities in 3D scans, right, or 4D fMRI scans as a basis for predicting the onset of cognitive decline or dementia? Very often these scans are large. Again, they are scale or gigapixel scale or even terapixel scale, and you have to go in and make sure that you're zooming in on the exact right region to find these types of anomalies in the MRI images, and that also becomes an important major challenge. So with that, I will thank the folks in the lab who done all this fantastic work, and look forward to questions. Thank you.
No.
No, that one. Yeah, that one. So you also had one block diagram type. I didn't fully see what is the reinforcement learning part, because typically for this kind of an audience, when you say reinforcement learning, what you're trying to learn is the underlying unknown dynamics of the decision process.
Right.
And you can explain on that. My second question on this was, so the Sasha 0.1 is 10% sampling, Sasha 0.2 is 20%, and the rightmost column is the upper bound because you're sampling everything. My question was, is there a kind of a knee in the curve? So if you make 20% or 30%, you would get into closer. What is the point at which there is a flattening out? Because the difference between 0.1 and 0.2 is very dramatic.
Correct. That's correct. Yeah.
So did you do any of this kind of studies?
So we did. Some of these results are presented in the paper. So there is typically at about 30%, it's data set dependent also.
Yeah.
Typically for these data sets, I think about 30% there was beyond which there was not that much use with sampling. But to go back to your first question, this is something that we've been asked many times. We applied RL here as one convenient way to do the sampling in a manner that would allow us to estimate the global state from sparse knowledge of the local state. So that is the only reason we did RL. But we did compare our method with other attention-based methods. So there are other types of methods that use what's called these attention scores themselves. So some method called ZoomML, for instance, that goes into each patch depending on how much attention the broader network is paying to it and zooming in, etc. We did better than those methods. So in fact, we did far better. So it suggests, needs much more exploration, but it suggests that for whatever reason, this RL-based approach is doing better than these types of conventional neural network based attention methods.
So RL in this case would be as you watch more and more images. Is that where the adaptation takes place?
That's right. So the state is getting updated each time the new patch is visited. So the global state is actually getting updated each time a new patch is visited.
Sir, I have a question. I'm assuming that the only information you had was the whole slide image and whether or not there is a tumor in the image or not.
Correct.
So how did you, I didn't really understand how you were able to train a classifier which can look at a patch of the image and whatever low resolution of the whole slide and decide whether there is a tumor in that patch or not, because you don't have that information at all.
No. Okay, so let me just go back. Sorry if I confused, said that confusingly. Let me just go back here. The classifier is not classifying at the patch level. The classifier is always classifying at the slide level. This is also multiple instance learning. We have never moved away from that framework. We're always in the framework of multiple instance learning. Why? Because exactly like you are, I think, hinting at, it is very hard to have patch level labels because histopathologists will take a lot of time to generate those labels. So especially in a resource constrained setting, we won't have access to those labels. So all of these predictions are made at the slide level. So this ST is this is a slide, this is not a patch. Every one of these things is a patch. Once you zoom in, it becomes a high resolution patch. And now the entire slide, the state vector associated with the entire slide is used to make a classification decision. It is not a patch level decision. Does that make sense? This is still MIL. We are still doing multiple instance learning.
So the state level vector is only updated through whatever zoomed in information that you give.
Correct. So each time you zoom in, you get more information, and then more information, more information. So like this, GIF that we showed, right? So I don't know if yeah, here. So I think this might be a bit intuitive. So each time you go to one location, not just that, but everything else also gets a little bit clearer. That's the idea. And why does it get clearer? Because of certain correlations that the model has learned. That if I go here, then I know something about the other parts of the image also, right?
Okay.
That's through training.
And how is it that you update this state vector?
So that's a slightly more complex question. So I'll give you a very quick summary of that, but we can talk about that in more detail. So just go forward here. So what we need to update the state is, so let me see if it, the low resolution information associated with all the patches, high resolution information, which is denoted here as V, associated with the currently visited patch, and the state vector of the past time step. Now, if I put all of these into an MLP and I try to predict the state vector associated with the future time step, for the current patch, I still have information associated with its high resolution representation, because now during training, right? During training, I have this capital V of C for that particular high resolution patch. So I compare those two, compute the mean square error loss, and update the state vector.
Okay,
Right.
thank you.
Hello, sir. This side. Yeah.
In the interest of time, we can take one more question. Okay.
I think there's a,
Okay. Okay. For extending it to epilepsy and seizure detection, usually how consuming it is compared to histopathology for a clinician to detect it, and these RL-based methods, how easy do you think the life can be made for detection, prediction, and even digitization for epilepsy and seizures?
are you asking a comparison between epilepsy and cancer?
Right.
So the main, again, I'll just give a brief difference, right? So in cancer, the image is static. So basically what you do is you take the image, you zoom into one location, and then you can maintain that state. Then you go to another location. You haven't lost information about the previous location that you zoomed in. You still have that information, right? Because you zoomed into that location. Then you go to a third patch and so on. So you can keep doing this. But in epilepsy, it's not like that. The data is streaming. So you go to one channel, you zoom into that channel, by the time you decide whether a seizure was there or not, new data has come in. So now you've lost, in some sense, that information that you had to make the decision. When the new data comes in, you have to decide now which channels do I visit in this new segment that has come in. So it actually becomes more challenging because you have to make predictions about the future, not about your current state. So that's where the difference comes in. We are obviously trying different things to solve that, but we'll see. We've not yet completed. So
Thanks.
yeah.
Okay. So I think this brings us to the end of Professor Sridhar's session. Let's thank him one more time. So we now move on to the third talk of this. Yeah, sorry. So I would now like to give a small token of appreciation. Thank you, Professor Sridhar. So we now move on to the third talk of this morning session. This is by Professor L.A. Prashant. I mean, you meet some people and you feel that, you have some long lost connection between them. So if you meet Prashant, you'll always get this feeling. And at least in my case, there is a connection in the sense that he is my academic cousin. He is Professor Bhatnagar's PhD student and I am Professor Borkar's PhD student. So we definitely have a connection. So today he will be speaking about policy evaluation for variance in risk-sensitive reinforcement learning. And to give an overview of Prashant, he is an associate professor in the Department of Computer Science and Engineering at IIT Madras. He was a postdoctoral researcher at University of Maryland, and he also had a second postdoc stint at INRIA. And he has written several books. In particular, he has written a book on stochastic recursive inclusions for optimization, simultaneous perturbation and methods, risk-sensitive reinforcement learning via policy gradient search, and gradient-based algorithms for zeroth order optimization. So I would now like to welcome Professor Prashant onto the stage. Thank you.
Okay, I like to move around. There's no body mic, is it? Okay, I hope I'm audible. Is this audible? Yes? Okay, so the current trend is deep reinforcement learning, and I'm trying to swim against it. So this is probably one of those solitary or maybe one or two of those shallow reinforcement learning talks. But to keep myself safe, I would like to say that all of these algorithms are easily extensible to the deep side. Yeah. And let's see. One of the problems that I faced by making these slides, always slide making is a traumatic exercise, is like whether I should do PowerPoint or Beamer. And eventually I figured a mixture distribution is better. So at the halfway mark, we'll switch to Keynote. And I want you people to wake up at that point, yeah. Yeah. So this is joint work with a bunch of people. Tejaram is a PhD student whom I'm co-advising with Krishna Janganathan, who is a prof at IIT Madras EE. Shubhada is here among the audience. She is in EC, IISc, and Shivatija is at Georgia Tech. Yeah. So a customary slide we are looking at, in case you forgot, we are looking at sequential decision making under uncertainty, and the bits are like states. You have states, actions, cost or reward based on your preference, and then state transitions, there are uncertain outcomes. And you have an objective, you either minimize the cumulative cost or the average cost or reward, and the job is to find the best possible policy. And because I'm doing risk-sensitive reinforcement learning, it is serious business. So for example, as a running example, you can keep this driving to work. This work was done during the pandemic. So technically there was no motivation then. But now we have moved on. Right now I'm in the heart of a city which is very well known for its traffic hassles. And so driving to work is amazing motivation, at least for the audience today. And the question now in Bangalore is, it's not highway. This slide was done with my US collaborator who preferred to use these freeways and highways. The equivalent in Bangalore is a ring road, and then there are gullies and local roads, the ring roads versus local roads. And whether you want to take the ring road or the local road, or you want to fly, it's up to you. Yeah. So the question is, like, you have the value function, and the value function, I think this was probably covered in RL theory by Guhan. It's the fixed point of a certain Bellman equation and all that. And the reinforcement learning job is to find a policy which will optimize some performance measure, which is, the underlying formalism is a Markov-Decision process. This is all, 101. And we'll be focusing on a very popular class of methods, policy gradient methods. You consider a class of smoothly parameterized policies, and you have a performance objective. You try to do gradient, maybe gradient ascent with respect to the objective. You're working with rewards. And there are some possible parameters. The parameterization is, application dependent. You could have this. And why risk? The real question is, why do you want to consider risk? I mean, in the investment example, maybe you people can become instant millionaires with some amazing RL algorithms very soon, and you take all of that money, go to an investment firm, and if the investment firm, the person at the investment firm, the investment banker tells you that I will make your portfolio grow 10 times in expectation, but there's a 5% chance of your entire portfolio being wiped out, how do you feel? Like, yeah. So if you are not risk seeking and if your risk covers, then you would care about such amount of money. And so there are, like, at least in finance and even in traffic commute, you care about the route that you take because maybe you have an important meeting in a different part of the city. That part of the city here is called Whitefield. If you want to go to Whitefield from here, and maybe you have a VC and you have some amazing idea, and then you get stuck. You get stuck for 2 hours, and so you lose a lot. So that risk of having a large delay, maybe with very small probability, these are things that don't come into picture when you look at expected value as an objective. If you look at expected value, these things are not given the right amount of weightage. So you want to incorporate risk. And in the risk neutral world, there is only one objective, which is the expected value. In the risk sensitive world, there are a whole bunch of objectives which may make people like me, keep people like me busy, because for each of these objectives, you can do RL and usually there'll be some challenge. Risk sensitive reinforcement learning, you will realize during the course of this talk, even for a natural measure like variance, risk sensitive reinforcement learning is difficult. It's way more difficult than risk neutral reinforcement learning. I'll try to make you appreciate all of this. Anyway, so in the traffic example, if you want to look at, so you want to optimize the delay, so you minimize the mean delay, but also, ensure that the variance is low, or the probability that you're stuck in a bad traffic jam, which is a bad event, you want to keep it low. The probability that you're stuck in a traffic jam, which is 2 hours, is less than, 0.001 probability and things like that. With 99.999% chance, you will go with a small delay or a mean delay which is low, and with a very, very small probability the traffic jam happens. Things like this, these can be coded as constraints, so you want to optimize this. So as I said, in the market of risk measures, there's a whole bunch of them. I've dabbled in many of these. Today I'll be focusing on variance, but as a thought process, if you have picked up RL background for students, then maybe you can try deriving TD learning or deriving a policy gradient theorem for some of the other objectives that I've listed here, which are not expected value. And then you will realize why things get challenging. So this is a somewhat controversial slide. I realize that, because you can do two things. You can optimize in a risk sensitive MDP, you can formulate it in two ways. One of them is like you minimize the expected value, assuming it is cost, and put a constraint on the risk, like some tail event or variance and things like that. The other is, you encode all the moments in your objective and optimize the risk measure directly. And this takes care of the mean and other things. One example is the exponential utility which someone specializes in here. And yeah, so whenever I talk about such things, I run into this particular talk, at least I won't run into that problem. It's like people have problems with having risk measure as an objective. Do you know the law that is against this? Anyone? It's called the Goodhart law. The objective itself should not be a risk measure. It's like, as an academic, H index should not be the objective. Writing good papers and then H index should be a byproduct. You should not have control over H index, hiring on H index. All of this, when gets based on H index, it's a problem. In the same way, you cannot do everything on a risk measure and optimize the statistic. That should come out naturally as a statistic and not the objective. But anyway, in this talk, I'm not doing that, so I won't anger someone. Yeah. So in case you forgot, we are looking at policy gradient setting with a bunch of parameterized policies, and we want to optimize some seamless self-plug. I wrote a book on this, so it's a very well-written book, thanks to my co-author. Please do read it if you want to get into this space. This is specifically risk-sensitive RL with policy gradients. RL is huge. You can do RL with different types of algorithms. You can be a Bayesian, frequentist. You can you can do plain optimization, you can bring in a control perspective, you can do a variety of things. We are focusing on only the policy gradient aspects of risk sensitive RL. It came out a few years ago. So this is the Goodhart law. So this is what? So when you do mean variance optimization, you are not violating the Goodhart's law. You're optimizing risk on the side while having a traditional objective like the mean. So it's still fine, yeah. And now the question is, when you think of a random variable like this, there's only one notion of variance. You look at that random variable, it has a certain distribution, and you can work out what is the variance. It's probability 101. Variance is defined like this. But the moment you come into an MDP, it's not entirely clear because you have a cumulative structure. You're accumulating cost, and these costs are random. And the question is, you're accumulating and you have a random variable which is a cumulative cost or an average cost. You could look at the variance of the entire random variable. That's one objective. Or you could look at how much each of these individual single stage costs vary from somewhere, things like that. So all of these are like legitimate, candidates for variance. I will show you two such examples to say that, again, to make you appreciate the fact that at the beginning, when you come into an NDP, even formulating a risk measure that is reasonable requires some work. So this is a running example. Imagine I parameterize this. So I'm going to, use this interchangeably, the policy and the parameter interchangeably. And now for any given policy, V is your usual value function. You maximize. This is a discounted return. And this G will be the variance. So now the question is, for any given policy which says how I choose actions, I need to figure how to, I need to figure a definition for variance. And the same thing for average cost or average reward MDP. So I changed everything to reward and I forgot this, so sorry about it. Yeah. So this is the random variable for a given initial state and a policy defined by theta, parameter theta. I have this random variable. One natural way is, since you are taking the mean of this, you could look at the variance of the same random variable. This is what I'm going to focus in the discounted part. And there's something similar in the average part, but I just want to say that this is like a variance of a cumulative reward random variable, but you could do something at each period and look at per period variance also. That's also a legitimate candidate. I'll show you those two variants in the average reward case. So this is the variance, and you can optimize this. And for optimization, an important part is how do you, evaluate this? Like how do you, estimate variance for a given policy? So in this talk, I'll focus only on the critic part, which is like you can use this as the inner loop or run it in parallel and do an actor critic algorithm where you evaluate, for a given theta, you evaluate the variance, you evaluate the mean, and then use these to improve your policy, maybe using gradient descent with the policy gradient theorem, all of that. I'm sidestepping the actor part in this talk, but it's all there in my book and a bunch of papers. You can catch me offline if you need references. Now for the average reward, again, this is a reward. This is the average reward. And now a per period variance is this. This is the average reward, long run average. And now I could measure how each individual reward, how far this goes from the average reward here. And this is one notion of variance. We'll call it stationary variance for a reason. It can be expressed using the stationary distribution of the Markov chain underlying this policy. The other thing is, you looked at this random variable with an expectation. You can look at the variance of the same random variable. Why do you change the random variable? These are two things. The important part to realize here is that we will see in the second half of the talk, which is a keynote presentation, is that these two objectives are not the same. Any guesses why they are not the same? Yeah? This variance and this variance. It's not, you have a sequence here, yeah. It's not about zero mean, but something else. Yeah. Okay, for a simpler case, Okay, we'll revisit this question. Think about this for half an hour. Yeah, think about this. Yeah, let's come back to this question. Yeah, keep your brain working. Yeah. So I'm going to zoom in on discounted MTP and try to make you appreciate all the problems that you face in variance estimation. So this is reinforcement learning, so I need to keep reinforcing the definitions. You know, attention is all I need. And yeah, not attendance, but attention. Yeah, yeah. So the mean, the variance. All right. There's something that I'm going to do, which is I'm not going to estimate variance directly, but I'm going to estimate the square value. I'll call this the square value, which is the expectation of the random variable square. This is a discounted sum. And V is your usual, you know, value function, which is a mean, and I take the square. So if I have an estimate for V, and if I have an estimate for U, I get the estimate for variance. And there's a reason why we do this, simply because if you go back to a very old paper in 1982 by Sobel, he showed that G itself has a Bellman type equation, or a fixed point equation if you want to be precise, but that's not monotone. So it doesn't lend itself to optimization algorithms. Well, policy improvement will not do policy improvement and things like that. Whereas if you work with U, this problem is sidestepped. So we'll work with you, and you'll also get a contraction. So that's one of the reasons we'll work with you and not G directly. We'll not look at the fixed point relation for G, but we'll look at a fixed point relation for U, which in turn depends on V. So both U and V together, we'll have a fixed point relation, we'll have an operator, all of that is coming. And the reason for that is we want to retain some nice mathematical properties, which is contraction, so that when I estimate, do stochastic approximation or temporal difference learning, I'll converge to the right place. Yeah. Okay, so value function, how do you estimate? You have an expectation, and this is a fixed point of a certain operator. You have, this is the Bellman operator, fixed point operator. This should be an R and all of this. And I can do TD0. This is the tabular version. I replace this expectation. I replace this, you know, if I expand this out, I'll get an expectation over the next state. I replace that by a sample, I get this. And this is the well-known TD0 algorithm. This can be written like this, where Zion can be seen as noise, and effectively I'm doing a stochastic fixed point iteration, very roughly. So that's really the idea of TD. The reason why I brought this up is because I want to do something like this for you. But for that, first I have to write down a fixed point relation which involves you, and then come up with an algorithm for you, and then try to analyze that algorithm. So, but before that, to set the notation, we have TD. Yeah, this is a nice enough algorithm. It does not require a batch. It runs, you know, and it bootstraps, and in certain words, it bootstraps. Now, this is the fixed point equation for U. This involves a V. Yeah, U is expectation of the random variable square. So you expect the V also to come here. So you have the reward square, and then the U of next state. So these two bits are like the usual fixed point equation that you have, you know, for value function. You have the one-step reward plus something of the next state. But because it's a random variable square, it's like reward plus something of the next state. I'll get a cross term also. This is the cross term which involves the value function. So when I look at it as an operator, I look at both U and V together. So I have an operator which will work on U and V together, and apply this RHS for U and apply this for V. So that's my operator for both V and U. And now the question is that a contraction? And the good news is it's a contraction. It is indeed a contraction. This is the operator. This is your V operator. This is the operator for the V, the value function. Single step reward, it's a bad notation. I forgot to replace all the K's by R's. This is the vector of single stage rewards, discount, and then transition probability and V. This is like V of the next state. But here, if you look at this bit and this bit, these are like cousins of these two, whereas this bit is a cross term. And this cross term has implications when we derive finite time bounds also. It's the cross term that makes our life difficult, even when we come up with TD. Yeah. No, both V and U. I'm applying, so this is the operator T theta. So when I take T theta, the thing is that, you know, for V I don't need U, whereas for U, I know for the fixed point equation involving U, I need the V. So jointly over V and U, T is a contraction. Jointly over V and U, simply because when I write down this equation, I have the V here. That's unavoidable, yeah. But the good news is this is a contraction. It's a contraction in some norm. You can look at the specifics, but it's a contraction. The implication is that I can do stochastic approximation, or in RL world, temporal difference learning. That's really the implication. Okay, so that's just this. So for, you take the TD0 for V, and this is the TD0 for U. And this, if you look at this, if you replace this by an expectation, if you go back 2 slides, I'll get this. So I'm replacing this by a sample. So I'm replacing this by a sample, getting rid of the summations, replacing by a sample. What I get is R square. What I get is R square plus U of the next state, gamma square into U of the next state plus 2 gamma into R times V of the next state, which is what I have. R square 2 gamma R into V of the next state plus gamma square U of the next state, and it's a fixed point relation, so I do minus U. So that's what I do, yeah. And for estimating U, I need the V, yeah. That's all I want to say, yeah. No, these are like the vector of single stage rewards, and this will be just trying to make a matrix out of it, yeah. Correct, over the policy, because I'm looking at randomized policy, otherwise just stack all the RSAs.
So
Like you have here, this small k theta in the V world is just, if you have deterministic rewards, R of S, if you have a deterministic policy, it's just R of S comma pi of S for all S. Otherwise, you average over the action, summation of the policy's actions probability times R of S comma that action, and something similar here. But K is a matrix, I need a matrix.
yeah, I'm just puzzled by the fact that this T2 is also a contraction, right? So in particular, there is like a 2 that is multiplying the gamma, and there is a k theta as well.
No, it's a contraction when I consider V and U together. I'm not looking at U separately.
I see.
It's V and U. The contraction claim is that there's a norm such that T of V comma U minus T of V prime U prime. That difference is, contractive. Yeah. So because solitarily I cannot analyze this unless I treat V as a constant. Because if you're going to make V variable and just look at U, it may become complicated. Yeah. So it's contraction when I look at both of them together. And in any way, when I'm doing mean variance optimization, I need to estimate the mean and I need to estimate the square value. So it makes sense to estimate V. It's not like I can get rid of V. Yeah. So I have V, I have U, and I have a contraction over that. And that just leads to this tabular algorithm in conjunction with the usual V update. So you put V and U side by side, you have the tabular algorithm, right? Yeah. All right, so the next step after this in shallow reinforcement learning is to use linear function approximation. And that's what is here. So you assume you have some features and you approximate it by a linear function. Why? Because we can do some nice theory. Deep learning folks can probably still do theory, but there are enough problems on the shallow side that I'm not compelled to go on to the deep side yet. Yeah. Now the question is, there is a V, and linear function approximation is classic for V. Now we are going to do the same for U, yeah, and we are going to use 2 different features. One of them is like square, the other is not the square. So imagine you have a phi V and a phi U. So different features for the V and U, value and square value. And now the question is, where does it converge? For V, when I do linear function approximation, this is the well-known TD0 with linear function approximations. Sitchless and Van Roy showed that, under some assumptions which I list, V will converge to the fixed point. This is the projected fixed point, which is also a linear system. You can just take it on faith here. What we are trying to do is what happens when I put a recursion for U together and look at V and U together. That's the next step. And that's here. So I have a TD error delta T for V and epsilon T for U. So these. And if you remember the increment, this is like a proxy for the value of the next state. This is the proxy for the value of the current state, and this is delta. And then this is your TD0 with LFA for the value. You do something similar for square value. For simplicity, I put constant step sizes, but if you want to apply a theorem from chapter 2 of stochastic approximation, then use diminishing step sizes. Yeah, and yeah, so this is here, and this is the increment that you saw. You have r square plus gamma square times u of the next state. I'm using this linear, these dot products as proxy for the u of the next state. So this is like v of the next state, this is u of the next state, this is the cross term, and here vt comes into picture. So for u, I require v, but for v, I don't require u. It's like that, yeah. So you have v and u together. So if I do a clubbed update, if I put v and u together as w, where does this converge? That is the question, and it can be shown that wt converges to w bar, and that w bar is also a solution to a linear system, which involves two fixed points. There's a fixed point for v, and we'll throw in a fixed point for u also. Yeah. And this may be too fast, so one of the feedback I got in classes, each time you throw an equation, spend 20 seconds. This came in my feedback, yeah, after the course, not during, yeah. So I make these feedback jokes, course feedback. In fact, in machine learning, I was even told that after making a claim, look at the students and try to infer if they understood, and then repeat the statement. So I should be a face reader, and I'm trying to do some face reading here, yeah. And I only see tired faces, sorry, yeah.
So right now you're only in the policy evaluation type.
No, I'll be in policy evaluation throughout this talk, yeah. I don't plan to get into, because I want to cover the average reward side of things. But in principle, I can write on a policy gradient theorem for theta and do fancy stuff. That's the actor part. It's there in the paper, but I'm not going to present it. So, assume rewards are bounded, features are bounded. There are two tall matrices that will come. These are like features for each state stacked up as rows. Yeah, these are two tall matrices, number of states times D, which is the feature dimension. And for each of the states, work out the feature vector and stack them as rows. And you assume the Markov chain, is ergodic, it's irreducible aperiodic, so it has a stationary distribution. Under these assumptions, with some diminishing step size, it can be shown that Wt converges to W bar, where W bar solves this equation. And this is a matrix, yeah. This is a matrix where, you have something. So if you look at the diagonal, this is something for V, this is something for U, but you have to live with the cross term here, yeah. And that cross term actually makes analysis challenging, getting a universal step size challenging, and things like that, yeah. So what this asymptotic claim was done, was done in 2016, almost a decade ago. Now, last year we managed to, I was able to sell this even in a machine learning conference. It's a side note where I had only asymptotic results. But in a sign of times now, I need to do finite time analysis to get through in a ML conference. So that's what I did, yeah. So in the long run, this is not my favorite author. I've not read anything, but when I Google, these are the most relevant quotes that I get for the talk. Yeah. Anyway, what happens in the short run of VAR-TD, a summary. I'm going to assume IID sampling, but as an aside, I want to say that all of these contributions can be extended to the Markovian sampling with a very neat trick, yeah, so it's not very restrictive in that sense. But there's data drop involved, it's somewhat suboptimal. But the important thing is, we want to understand what are the rates that I can get and whether I can get it with a step size that does not depend on information that are typically unavailable in a RL setting. So I'm assuming the algorithm is given the state, reward, and next state, these in an IID fashion, where I pick the state using the stationary distribution of the Markov chain underlying the policy, and then pick the next state using the transition probability. So I'm not assuming access to this. I look at this data set and then run my TD, VAR-TD for some number of steps. This is the IID sampling, but with mixing, I can tweak this. So with mixing, what happens is initially there'll be a transient period. After that, the stationary distribution kicks in. So that will induce one extra error term. So you can handle that directly in the analysis, which we didn't do, or you can handle that with data drop by looking at samples which are like mixing time apart. So that comes down to the IID setting, which is the trick that, you'll have to look at the paper to look, check what the trick for Markovian sampling is. Anyway, the important thing is, now I have an algorithm that can be shown to converge to W bar under some assumptions which are very similar to what you do for TD with linear function approximation, vanilla TD. Even for variance TD, it's the same, it's like similar assumptions. We are not adding any extra restrictive assumptions. Now the question is, in a finite run, like, I want bounds like this, mean square or root mean square bounds, which are like this, or high confidence guarantees in this form. I want this, and the question is, and here this alg, I mean, it's like it could be last iterate or an average or a tail average and things like that. So this can be, I run the algorithm for t steps. After running it for the t steps, I can give bounds for the last iterate, or I can average the whole bit, all the iterates, or I can look at average only, a last portion, like last 10% of the iterates I can average, because the idea of tail averaging is like initially you may be in a, at a point which is really bad, but after a while you get close to the limit, so it makes sense to average after a while, not from the beginning. That's the tail averaging intuition. So we are going to look at tail average bounds and also last iterate bounds and show the benefits of tail averaging for variance TD. So that's really the takeaway at this point. Even if you don't understand the formulation of variance TD, you can still get something from this talk by understanding the fact that I have solving a linear system like this, but I'm not having access to M and Xi directly. I'm not solving this linear system directly because M involves the stationary distribution of a Markov chain and also the transition probabilities of the Markov chain. We don't know any of this. I'm solving this indirectly using stochastic approximation, also known as temporal difference learning, and trying to get this finite time bounds. Yeah. So this is in the spirit of linear stochastic approximation. So these rates are insightful for linear stochastic approximation. Yeah. In case you forgot to memorize this matrix M, this is it here, and this is the last iterate bound. So after t steps, this is the bound that I get. This is the initial error. W0 is the point where I started. W bar is the limit. And this goes down exponentially. Because I have a constant step size, it is expected that, there will be a constant addition. The error won't go down. The variance will matter. Yeah, variance will matter. This is the last iterate bound with a constant step size. The real problem is this. Under assumptions where, if you assume those two tall matrices features have linearly independent columns, full column rank, then this assumption can be easily verified. Yeah, there is a certain mu for this matrix M, and this matrix comes into the picture because this is the linear system that you're solving. And you're looking at a certain minimum eigenvalue of a matrix, for which you're trying to solve a linear system of equations involving that matrix. So if my step size alpha is less than mu by some constant, then I get this bound. Otherwise, I don't get this bound. But mu is typically unknown. Typically unknown in a RL setting. So how do I get rid of mu? Yeah. See some constant. I think we'll have to look at the paper. Yeah, for some constant that depends on bounds on the features and rewards and the discount factor. Let's say I don't remember. I don't have it on top of my head. It's been a year, but it does not depend on any other unknown quantities. C can be treated as a C is like information that's available. Yeah, probably. Yeah, but the important fact is I need to know mu. I need to know mu to get this bound, and this is typically unknown. And one way to work around this is to do tail averaging. So I'll explain tail averaging. So this point K is the point where I start averaging. From K until T, the last iterate, I average. So I average T minus K iterates, the last T minus K iterates. If you want to look at an example, you can put K as T by 2. So I'm looking at 50%, or K is some fraction. So the last 10%, 20%, or one of those percentages. Then you will get this as like 1 by some constant times T. That's the last percentage of iterates. If you ignore the percentage, it's like some fraction, that's some constant multiple of T. For this, I get this bound, but again, I have a problematic mu dependence in the step size, which I forgot, which is hard to specify because it's a very bad equation, but to get this bound, the step size alpha depends on mu, the same mu that I had before. What is perplexing is that, a similar result for vanilla TD, I was able to get rid of mu dependence for vanilla TD with tail averaging. I didn't have to, so for vanilla TD, And if you dig down, what happens is this cross term is the killer. The cross term actually makes it very difficult to get a step size that is universal. In the case of vanilla TD, we were able to do some algebraic tricks eventually to bound something and get rid of the mu dependence using tail averaging. And I can only give you an intuitive argument that because of the cross terms, such an approach is not feasible for variance TD. Now, given that it's not feasible, the only other alternative is like you want a minimum eigenvalue here. If you remember, you want a minimum eigenvalue here. And this mu you don't know. So the only alternative for this is what people do in machine learning, like training, and if you don't have strong convexity, you make it artificially strongly convex. So the word to be used is regularization. You solve a regularized setup, you solve a regularized system of equations, and you can get a universal step size. And the regularization constant that I use, I'm solving this, instead of empty, I'm going to throw in a zeta, and this is like a proxy for mu in my step size setting. I'm going to use zeta as a proxy. And when I do that, I'll get a universal step size. And note that this system, when I solve this, if I solve this system with m plus some zeta I and equal to 0, that will give me a solution. That's not W bar, but the bound for regularized, variance TD is to W bar, which is the unregularized solution. It's the original system of equations. And the way we do it is like we show that this W naught, wherever I start, is close to the regularized solution, but this regularized solution itself is close to W bar. And that's like order zeta square. So we choose a zeta carefully and get an overall bound that's like 1 by T minus K. Yeah, so the point is, apart from getting a universal step size, if you want to get a bound which is like 1 by T minus K, put K equals T by 2, you will get 1 by T bound. If you want to order 1 by T mean square error bound, then you can choose a regularizer like this, plug it into the bound. So for any zeta, I get a bound, and then we optimize, and we saw that 1 by square root T minus K works out. So you can achieve a universal step size. You don't need, here the step size does not require eigenvalue information. It only requires a bound on the features and the discount factor. It doesn't require anything extra. Yeah. So that's really the important conclusion. This was published in RL conference. Yeah. Huh. No, the point is I choose an adaptive zeta. I am controlling zeta. I am solving a regularized system. Mu is unknown, but there's a mu. If I assume some matrices, if you go back to the assumptions, which is a long way, if I assume these matrices have full column rank, that means there is a mu greater than 0. There is a mu. But I don't know that mu. It depends on the rank of this, the stationary matrix, what's the minimum entry, and things like it's typically unknown in RL. And no algorithm uses this information in practice. But what I'm saying is, because my analysis requires mu to get these bounds, I'm going to make this bound for a regularized solution and show that the regularized solution is close to the unregularized solution with the order zeta square. That zeta I'm going to control so that I get a overall 1 by T bound. That's really it's like triangle inequality. Yeah. Yeah, that maybe doubling trick works. I honestly don't know. Yeah, we have a horizon dependent thing. In RL, we don't have any time theories yet. Maybe some of you can come over there, and then the next time I write a paper, I'll also have a anytime bound. At this point, I'm able to sell with horizon dependence. The question here was, if all of these parameters depend on T, like if I don't set zeta like this, I don't get this bound. So I need to fix the horizon. But the way to work around this is you want to make this mean square error less than epsilon. So you can work out a horizon and work backwards like that. That's a somewhat slightly satisfactory answer, hopefully. You just want to make this less than epsilon. Yeah.
Thanks.
Yeah. Going back to the original problem, I wonder if you did it in a 2-time scale fashion, right? Would you be able to resolve it? Because you have a V and a U, right? So if you first find an estimate for V, and whatever that estimate is, you fix it, and then you find an estimate for U, because in that operators that you had, if you fixed V, I think with respect to U, you had a contraction like gamma square P theta something. So I guess something like that should
may be possible. Yeah, that may be possible. But the point is, at the beginning we wanted to do everything at a single time scale, but maybe that can be worked around. Like our goal was to see if I can do something in single time scale itself. Yes. Yeah. I mean, to get the optimal rates, in any case, you need to know the minimum eigenvalue, right? Can you get rid of that? Honestly, even then there will be a certain mu that you don't know.
No, you will have to use iterate averaging for the
Yeah, you have
U
to use
update.
averaging.
Then
So then you can use tail averaging also
Yes.
there. I can use tail averaging. Yes, that's entirely feasible. The problem that we got was because of the cross term. If I fix V, then this system is manageable. Yeah, that's entirely possible. Yes.
And in this regularized thing, at least if I'm not missed anything, it looks like the solution to the regularized problem is the same as the solution to the unregularized.
No,
one.
no, this is the solution to the regularized problem, which is you go back here and add a zeta times I here.
No, but as you take t to you have to take
No,
zeta
I'm doing all of this at a finite
IISc.
number of
Okay.
runs. So I'm going to solve, you tell me the epsilon, I'll tell you the zeta.
Sure,
Yeah.
sure. Thank
So
you.
there is a zeta, and so this W reg, whatever I have, is different from W bar. W bar is the unregularized solution, this W reg is this, and that's bounded, the difference between them, this, say W bar and W reg, this square, is bounded by order zeta square. So that's where we play around. Yeah. Okay, there's a seamless self-plug, there's a lot of zeroth order optimization happening. This is also relevant because the actor for this, if you write down the policy gradient theorem for U, then you cannot do the regular policy gradients. You will realize that you cannot do regular policy gradients for a reason, and then you will have to come down to zeroth order optimization. So that's where, for the actor, if you want to understand, you can read this fairly recent book. Yeah. And this work, whatever I presented, policy evaluation, even the actor bit is in RL conference. I just have to, this work was done last year in January, and there were like half a dozen deadlines around January end, and a student in this audience asked me, what do you think about RL conference? As a typical, machine learner, I thought I should get a sample, so I submitted to RL conference. So if you have any new conference suggestions, you can suggest. I will definitely try, as long as, people who promote me care about these conferences. Anyway, so the other part, which is vanilla TD, tail averaging bounds, you can look at this paper a couple of years ago, and this is an older one with only asymptotic results. And the other work, which is here, this is what I'm going to present next. I'm not done. I'm going to take a cue from Professor Vidyasagar. I thought I should have at least 100 slides. So I can keep talking. Yeah. So one of the problems that we are facing now is overthinking with all the ChatGPT and whether I lose my job, or what will happen to CS professors if we lose our job and all that. So I took this is not ChatGPT generated, it's actually a real poem by a real person. And there's a pharmacy where a pharmacist will give this poem as the medicine for real people, human beings. Yeah, that's what it is. Anyway, so I want you to keep your presentation manners, don't doze off, because there's an entire second half waiting. And this is where, it can be jarring. And I'm convinced that it may be better to not have one theme for the presentation, only Beamer or something. You have to keep switching between multiple themes so that, it is jarring, and you have this movies where, with strobe lights, people have warnings. So it should be like that, it should be troublesome for your eyes, and you should not sleep. So that's what happened here. So this is part 2. I'm going to look at variance estimation in an average reward MDP. And this is total variance. So we'll go back to the question that I asked, what happens in an ergodic Markov chain and what happens in the IID case. So imagine you have a Markov chain, take the simplest case, finite state, yeah, and you have a bounded function, and you're looking at this quantity, yeah, you're looking at this quantity, which is an average. And this will converge because, you have assume finite state irreducible, so there is a stationary distribution, and this will converge to the yeah, stationary mean. Let's call that f bar. And then you have this central limit theorem type result. You expect this quantity with 1 by root n scaling to converge to a Gaussian with mean 0, obviously. But what is the variance that it will converge to? In the case of IID setting, this quantity, you have only one distribution, and you have a mean of that distribution, and this is the variance of that distribution. So this quantity, Sn minus n times mu by square root n, this will converge to a Gaussian with mean 0 and variance, which is the variance of this. We'll call this the stationary variance for, let's say, because there's only one distribution, it's not changing. Whereas in this case, it does not converge to that. It does not. Yeah, it does not converge to the stationary variance of f. It does not. Why? Any guesses? Sorry? I don't know who is talking. Can you raise hands? It's too far. Okay, I'm slightly old, not very old, but yeah.
It's not independent, so you can't write variance of sum equal to sum of variance.
Yes, that's the equation that I'm going to throw in. These are slides that thankfully I didn't make. These are fantastic slides made by my collaborator Shubhada. I've just arbitrarily chopped some things off and tried to keep it serious. That's the only thing. Yeah. The first half, whatever was my contribution in terms of slides. So there is covariance. So if you look at variance of x plus y, you have this covariance. In the IID case, there's no covariance, so you'll get the variance whatever you're looking at. Here, you will not get it. You will get this covariance term, which looks like this. It's like saying what happens after k steps given that something at x. How x0 relates to xk in terms of function values. This is what comes into picture. And what we are interested now is trying to estimate the variance, the kappa of f. F is fixed. You want to estimate kappa of f. You are given a sample path of the Markov chain. Given a sample path of the Markov chain, you want to estimate kappa of f. I think the RL connection, which I'll not, make it extremely precise, is like if you fix a policy, you'll get a Markov chain, and for that Markov chain, whatever I do here will be relevant. It will have so I'll call this the asymptotic variance. This asymptotic variance can be split into the stationary variance plus some correlation terms. Yeah, covariance terms, correlation terms, whatever you call this. So this part alone, is the stationary variance that I looked at. If you look at per period variance, how much it varies, then it's like the stationary variance. If you look at the example that I gave before, where in an average reward MDP, I fix the policy and I look at how far each single stage cost is varying from the stationary mean. If I look at the square, then that's the stationary variance. But that's not the variance of the random variable that you're looking at. The variance of the random variable that you're looking at is involving these covariance terms. So there are two notions of variance. One of them is asymptotic variance, and that includes the stationary variance plus covariances. Yeah, 10 minutes, okay. And this can be written with, by like this with some simple algebraic manipulation by using the fact that covariance of f of x0, f of 0 is this 2 times this, so I've adjusted this. Yeah. Now, the thing I want to say is, as part of ICML, we required double sampling, to do this estimation, which is like I needed two independent sample paths because of the fact that I had an expectation of 2 terms, and there was no easy way to work around. And thanks to my co-authors, they found a way to get rid of this double sampling. So post ICML, you can look at the draft on archive. We have a single sample path based algorithm. Single sample path based algorithm, and the important thing, this has received a lot of research attention in a totally different community, and the important message is they do what is called as batch means. You take a trajectory, cut it into pieces, do something for each piece, and come up with your estimator. That's like the most layman way of putting things. Many of these are batch estimators, not online, and they require a lot of memory because of their batch nature. There's one online estimator. For the batch estimator, you can ignore the log factors 1 by n mean square error bound. But for the online one, to the best of our knowledge, the bound is weaker. You don't get 1 by n bound. So you either have to use up a lot of memory to get a bound that is nice and a batch algorithm. Or you have an all-in algorithm which is a weaker bound, and our work closed this gap. Our work closed this gap. I mean, there was an asymptotic bound of the order like this. So we have a non-asymptotic bound O of 1 by n, which is online. It does not require O of n memory, where n is the sample path length. Yeah, that's really the way to put this. So what we do now is we take this variance and relate this covariance terms to this V, which is the differential value function that comes from Poisson equation. Now I'll zip through, but I think you can, if you're sufficiently interested in this work, you can check out the paper. So the important thing is this is not the value function that you see, there's an extra twist. So this is coming from a Poisson equation because you're looking at an average, or you're looking at Cesaro averages in a Markov chain, or even in average reward MDPs. You fix a policy, you have a Poisson equation. So you can relate this to the Poisson equation, bring this term, and so what happens is ignore all of this. So the point is kappa, if you look at this, kappa, which is what I want to estimate, the asymptotic variance is expectation of something, where this is the long run average reward, and this V is the differential value function, which is a solution to a Poisson equation. So what we do is we'll do stochastic approximation to estimate kappa, and for each of them we'll use well-known bits. For V there's a way to estimate, so it's like Poisson equation can be turned using stochastic approximation, and then you can use a simple averaging recursion to estimate F bar. So that's what we do. I'm going to skip the stochastic approximation 101, and this is what I do. So for Poisson equation I'm solving a linear system like this. And for kappa, this will converge to expectation of g of x, where the g is this big bit. So, yeah, and I need 3 auxiliary quantities. If you look at this, I need 3 auxiliary quantities. I need an estimate of the differential value function. I need an estimate of the mean, or what do you call this? I've forgotten the name. It's like average value function, which does not depend on a state value. Differential value is a function of the state. You take stationary average, that's V bar. So I need V bar, V, and also the average reward as a running average. If I use these 3 bits, then based on the sample path, each time I look at a new state, each time I look at a sample transition and measure f of xn, which can be cost or reward, then I'll do a O of 1 update to get an estimate for kappa. So each update is O of 1, it's constant time, does not depend on n, and we use this as the update, where each of these bits you can estimate like this. So you are solving this A, V plus B equals 0, you get this. And then you have stationary mean estimation for F bar. This is just mean estimation. And then if you put all of this together, I get the last bit, which is the variance estimation. All of this is on 1 time scale. I don't need time scale separation. All on 1 time scale. Yeah, there are no circular dependencies or coupling. And the main message I want to show before I wrap up is that our estimate can be shown with a lot of effort. We can estimate, we can establish a order 1 by n mean square error bound. Yeah. So if you want to make it less than epsilon, yeah, you have to choose a n which is order 1 by epsilon square. And we also characterize some quantities which depends on the Markov chain in this O. We don't hide them. Yeah. And there are some things that I didn't discuss, which is we have extended this to linear function approximation, and also applied this for average reward reinforced learning. You can look at the paper draft. At this point, I'll thank you all. Yeah.
Thank you, Professor Prashant. So we have time for a few questions.
So Dilbert got cancelled, so you won't get this comic. So you can ask me, and behind a payment firewall, I'll send it back to you. Until recently, I don't know, until last year, it was around, but now you won't get Dilbert comics unless you have them somewhere.
Yeah, hi, I'm here. In the average reward case, are you implicitly assuming unichain, that Only on the DAT?
Irreducible, periodic, all of this. The whole starting business is here.
Okay.
It's explicit. I need a stationary distribution, I'm assuming it. Yeah.
How hard would it be to relax the assumption? Like, what would the technical difficulties be?
How hard? I've not thought about it. Shubhala, you have any thoughts on that? Somebody give her a mic. Maybe you can have a reducible Markov chain, do something for each.
Yeah, so the solution of Poisson equations existence is what we need for the estimator to work. We need some properties of the solution, and you can relax ergodicity to some extent, but not completely. Thanks.
Yeah.
And in the discounted reward results, so for the regularized finite time guarantees, it was unbiased in the sense that if you take t to infinity, it dies down to 0. But in the unregularized version, it is biased, the finite time analysis.
No, I mean there's no bias. The unregularized version also, the bound is to W bar. And if I put k equals t by 2, I'm getting order 1 by t bound in either case.
Oh, okay.
I'm getting order 1 by t bound in either case. The problem is that to get this bound, I have to set a step size alpha that depends on mu. For the unregularized case. For regularized case, I got rid of that problematic dependence.
Okay.
I'm getting O of 1 by t mean square error bound with tail averaging in either case, unregularized or regularized, for the same W bar, which is what I'm trying to get to.
Okay. Thank you.
Are there any more questions? Maybe I'll ask one question. See, okay, yeah.
Sir, did Markov chain make use of fairly distribution or unfairly distribution?
Sorry, what distribution?
Fair distribution or unfair distribution of data as such?
No, I'm just saying my sampling is like this. If you look at this IID sampling,
Okay.
where I had it.
So,
Yeah. So I'm assuming the existence of a stationary distribution, which is given by psi. And my data set is formed like this. State,
Okay.
reward, and next state, where I pick S from stationary distribution, which is known to exist for irreducible finite state Markov chains, and then I pick the next state using this. So I don't have closed form access to this, but I assume this data set is formed using this logic.
okay, thank you.
Yeah.
Okay. So maybe in the interest of time, I request the audience members to ask questions during the lunch break. I would now like to give a small token of appreciation. Okay, so this brings us to the end of the first session. We'll now break for lunch and we will reconvene at 2 p.m. We have 3 exciting talks in the afternoon session. Hope to see you all there. Thank you.
Speaker for this session is Paras Chopra. He's a founder of LostFunk, a lab based out of Bangalore, where independent researchers explore foundational questions in AI and beyond. Prior to this, he founded Wingify, a market-leading SaaS company from India. So with this, let's welcome Paras. He'll be talking about MetaRL. Welcome. Yeah.
Awesome. Am I audible? Great. I think I have the difficult job of waking everyone up after that amazing lunch here. Hopefully, my talk will do justice to this difficult problem, and I can share my joy for everything meta. As you can see, the title of my talk is Meta RL. For some reason, I just get fascinated whenever the word meta goes around. So we'll see what all is happening there. But first, a little bit about Loss Funk. So Loss Funk is just, we are just new kid on the block. We are an AI lab, AI plus more foundational questions. In fact, anything that just strikes curiosity at a foundational level, we are trying to pursue that. About 25 full-time researchers, most of them research interns, but some of them research fellows who've sort of quit their job and now working with Loss Funk to explore, different questions. So this is the outline for the talk. First, we'll just talk about what in fact is meta-RL. This word could mean so many things for different people. So we'll just spend some time doing taxonomy of it, defining it. Then I'll talk about why it's great time to get into meta-RL in 2026. Then we'll review some major breakthrough results in 2025 that really had people sort of pay attention to this field, and some of the early experiments from my lab, and then open questions in the field. So whatever work in our lab is being done, which I'll present, is done by Akshat Jaswal, who's also here. So you can perhaps catch him with some of the questions on the coffee break. Awesome. So I guess the whole history of the field of machine learning has been climbing one level in abstraction every couple of decades. So we literally started with these expert systems where you had if, then, else, and a huge list of if, then, else that made different systems go around. Chess to recent times also, Stockfish and etc. else was mostly just if, then, else. But then with, let's say, kernels and support vector machines, we started doing moving away from if, then, else, and we started learning from data. And that was when we started hand engineering features. So great features, you could sort of separate even nonlinear data if you do the right kind of feature engineering. But then deep learning happened where people said, I don't even care about feature engineering anymore. Let me learn the right features and light representations from the data itself. But the algorithm is still fixed. All of us know what backpropagation does, what PPO does. But I think we are now coming to a time where we are stepping one step further in abstraction layer, and people have started asking, why even stop there? Why even stop at just having fixed algorithms? Why not just discover learning algorithms themselves? And of course, all of this is motivated by this gentleman here, which I'm assuming all of us would know, Richard Sutton, who's written this beautiful essay, very short, compact, called The Bitter Lesson. Most of you may have read it, but if not, I strongly recommend to go ahead and read it. It's just a couple of paragraphs. And there he sort of just makes an observation. It's of course not a law. It's not a law like the Newton's law or special relativity, but he makes an empirical observation that most of the advances in machine learning and AI have come from methods that can scale with compute. And the history has shown that all the ingenuity that humans have put into handcrafting different aspects of the machine learning pipeline, you throw more compute at it, and that more compute sort of ends up powering the handcrafted ingenuity. And he obviously says, that two methods that seem to scale arbitrarily in the history of machine learning is search and learning. So with that background in context, the bitter lesson, let's define meta-RL. So meta-RL simply is, designing systems that can learn how to do RL better. So that's what the meta really is doing here, where instead of doing reinforcement learning yourself, could you design a system that does reinforcement learning and actually becomes better at reinforcement learning? So as a schematic, this can help you understand difference between traditional reinforcement learning and the meta reinforcement learning. So on the left is obviously the diagram that all of us would know by heart. You have an agent that does some action in environment, and you get reward and next state, and based on that you iterate the policy of the agent. But in meta-RL, what you do is you in fact have these multiple instances of the loop. So you see there is an inner loop and an outer loop. In the inner loop, you sort of initialize the inner loop using some parameter. It could be any parameter. For example, if you're trying different loss functions, you can imagine each of the inner loops gets a different loss function, and then the agent sort of takes that parameter, the meta parameters, and does RL on it, the traditional RL, and then the meta loop iterates on that meta parameter based on what helps you get the total amount of reward. So hopefully this is clear, but if it's not clear, by the end of the talk, I think this will become very, very concretized. But if you have to keep one thing in mind in meta RL, it's just that it's like traditional RL, except that you are varying some parameter of the whole RL process and launching multiple instances and learning over those multiple instances instead of having just one instance. So as a rough intuition pump, you can think of what a human researcher does, where you're constantly tweaking hyperparameters or making changes in the algorithm and seeing what happens. You're in fact just automating that. So instead of a human doing these things, you're just automating it. So of course, there's multiple things you can meta learn, right? The whole RL pipeline is rich enough that it can allow you interventions at multiple levels. One of course is you can learn a policy for fast adaptation, and we'll come to what it means, but it's the classic meta RL wherein you're learning like a set of parameters where at inference time you can get to like an optimal performance with as few samples as possible. And then the second, you can learn parts of the RL loop itself. So you have loss, objective, optimizer, reward, and different kinds of things, and you can try to learn what's the right right sort of component for me to use for my problem. Third, you can learn the update rule end to end, wherein you just throw most of these things and say, let me just learn the whole RL algorithm itself. And lastly, you can use LLMs and search to literally synthesize code, which is now possible to do so. So as I said, why is it great time to do meta RL? I think two trends are sort of just pushing us into the direction of learning how to learn itself. One is that now we have GPU based environments, and the second is now we have LLMs as evolution operators. So GPU based environments, most of you would know that the traditional RL environments are CPU based. So if you've ever seen Atari environment, OpenAI Gym, etc., all of them are CPU based. So what CPU based means, it's literally your CPU is sort of just going one state at a time. You act on your environment, you get a reward computed from your, it's almost like, a game is running. I mean, it is, in Atari's case, it's literally the game is running, and OpenAI Gym, where you have Cartpole, etc. It's also in most of the environments are actually just CPU based, where the max parallelization you can do is just, use all your CPU cores. So if your CPU has 8 cores, the max you can do is 8 environments in parallel. But with GPUs, now you have environments where the whole environment dynamics are written in GPU, which is just like a bunch of matrices. What that allows you to do is you can literally run thousands of environment instances in parallel. Because with meta RL, if you know the inner loop is all about launching lots of these inner loops in parallel. So the more kinds of experimentation you can do in different whole RL runs, the faster you'll get. And GPU based environments let you do that. And the amazing thing also is that if you are doing this deep reinforcement learning where your model is running on GPU, so if your environment is also running on GPU, you just have no overhead in transferring the memory, where generally the CPU GPU bottleneck is usually the memory transfer. So to give you a flavor of what these GPU based environments look like, of course they are not one-to-one replicas of CPU based environments. But if you have ever seen syntax of, let's say, OpenAI Gym, you would see that the syntax is pretty similar. So it's sort of like if you have like your RL problem set up in PyTorch, etc., the environment is just drop-in replacement, and the speedups are insane. So if you see number of seconds for 1 million steps, it's literally like on the order of, I think this is milliseconds, 7 milliseconds for million steps. And this is how one of the environments, which is a replica of Atari Breakout, looks like. It's called, I think, Minitar. The amazing thing is that because these run so fast, you can collect 1 million samples in 7 milliseconds. You can just do a ton of experimentation on your RL problem at just speed which CPU-based environments can just not afford you to do that at all. Some more environments. There are lots of GPU environments that are cropping up. You can have a GPU-based environment of board games. So you can have backgammon, chess. All of these are entirely running on GPU, which is extremely fast. You can have optimization problems like bin packing, shortest path, etc. And then, of course, there are robotics environments where you can have humanoid and robotic dogs, etc. So GPU-based environments are possible literally in last 1 or 2 years, which is accelerating it. And the second accelerator of meta learning is LLM guided evolution, which is again literally been possible as LLMs have become better. Because earlier, if you know, evolutionary algorithms never took off because you need to have very well-defined grammar, and these algorithms could only work on those grammars. I mean, evolutionary algorithms are nothing but you take what's working really well and you fuse them. But if you fuse them and get a child in a very sort of naive way, most likely you will just break. You can't just take 2 pieces of Python and just merge them without knowing their semantics, etc. But LLMs are really good at that, right? With LLMs, they can very intelligently sort of merge 2 programs. At the core, LLM guided evolution is just this very simple loop, which is you give the code while it's not optimal, you mutate it, evaluate it, and you keep passing feedback of your code to the performance of it, what worked, what didn't work, back to the LLM, and it'll just keep on making changes. Of course, what got everyone pay attention to evolutionary algorithms using LLMs last year was AlphaEvolve. It's not open source, but at the core, it's just extremely simple. And if anyone of you want to write a version of it, you can write it in 100 lines of code. So what you end up doing is that if you see this pseudo code, you have like imagine you're trying to improve upon PPO algorithm. What you'll do here is you have like a database of RL algorithms. Let's say you have PPO and a couple of others. Then you sample one of them, and then you have like a prompt sampler, which is nothing but instruction to an LLM on what to modify. So you can imagine some instructions to be like intervene at math or think of neuroscience ideas. It can be anything of that sort, right? And then the LLM takes that prompt and generates a diff, which is like what changes to make. And then it generates like a child program applying that diff to the parent program, which could be like PP or any other algorithm. And then you run that in that meta loop that we talked about, which could be like a GPU-based environment. And then you add it into the database along with the results. So literally is this simple loop that ends up driving, changes and improvements to the current algorithms. If you want to try, there's some open source versions also. There is this OpenEvolve and ShinkaEvolve. You can see very similar again the process. You take program, you ask LLM to do something, you evaluate the performance, and then you just keep on going in the loop there. So let's go through some of the results in MetaRL. It's just a tasting menu because of course the field is so vast. I won't be able to cover everything under the sun. But let's go through the taxonomy so that you build intuitions on what all interventions are possible, what all can you meta learn. As I said, the first is that you can learn the policy for fast adaptation. This is of course known by different things, but model agnostic meta learning, where the idea is simple, and this is like an quote unquote old sort of approach where you have what you do is that you sample tasks. It can be different environments, and the whole idea is that you then split the data into 2 parts. One is support and query, and then you do like gradient steps on a part of data, but then you evaluate loss on the other part of the data and back propagate it. What it does is that eventually it gets you like a set of parameters which are optimal for fast adaptation, because that's what you are training the whole pipeline for. Which means if you've trained this whole pipeline on 10 environments and you at inference time you get an 11th environment that you've never seen before, then hopefully only with few samples you'll be able to do a good performance of it, because your whole incentivization in this training loop was fast adaptation. So that was, you can learn policy for fast adaptation, but you can also learn parts of the RL loop For example, what you could do is you can learn an optimizer itself. I mean, we know there is optimizer in deep learning like Adam and new ones like Muon and stuff like that. You always need an optimizer when you're deep learning. But if you think about it, an optimizer is simply a mathematical function that, takes in gradients and gives you the delta of parameters, which is the updates. So literally that is Adam, that is what it does. What is the gradient and what is the parameter update I need to do? And you can replace that mathematical equation with a neural network. And what you have is what they call as learned optimizer, where you are learning the optimizer itself instead of just taking an optimizer from the off the shelf. And you can then train the optimizer on this reward, which is from sum of average rewards or the total rewards in the inner loops. So over a period of time, your optimizer ends up learning what's the right gradient updates to do for your RL problem. And this is the paper where they sort of showed that they learned an optimizer called Open, and in RL problems it's ended up sort of outperforming a couple of other popular ones like Adam, etc. And the interesting bit was if you see some of the things that can be meta learned in this one particular paper, they tried to meta learn the function loss itself. So if, for example, if you're doing PPO, you need to predict in the sense the value function, the value of a state, then the MSE loss, which is L2 loss, is quite popular as a formulation where you sort of you try to sort of minimize the distance, L2 distance between your predicted value and the value you want as a target. But is L2 the right one? Can you replace that with a neural network and learn the loss function itself? And they did that, and what they found out was, I mean, of course, if you see PPO with L2, that is blue. But if you do PPO with the meta learned loss function, it is on orange, which you can see it sort of converge way faster. But the interesting bit was if you analyze what it learned, it's actually very different from L2. A, it's not symmetric. You would expect L2 to be symmetric. And B, of course, it's more or less like linear instead of exponential, which you would have L2. So again, the lesson I want to keep bringing is that this is a bitter lesson in action, right? We've spent so much time in building handcrafted loss functions, value functions, etc. But if, and that's a big if, of course, if you have access to tons of data, then you can learn all of these things end to end, which people have started doing it. So these couple of results were something which people had been doing for a few years now, let's say on the order of 5 to 10 years. But next set of results are which are literally come last year, and we'll review some of those recent breakthroughs in meta RL. As I said, coming back to the taxonomy of meta RL, the third thing you could do is you can learn the update rule end to end. And I'll clarify what I mean by that. But the really big breakthrough was this paper by DeepMind again, that they published in Nature, where they discovered RL algorithms that beat all the standard RL algorithms on Atari and a couple of other environments, which was learned end to end. Their core insight was actually quite counterintuitive. And this paper took some time for me to really grapple with what the hell they were really doing. And I'll try to do justice to it. But just please raise your hand and ask if something is not clear. What they did was they replaced the traditional handcrafted targets with learned targets. What it means is that if you have standard RL, let's say you have TD learning, you have your network make certain predictions, which is the value of a state, right? And you have like a target, which is the actual reward that you get and discounted value of the next state. And you minimize the distance between these two. What they did was instead there was a meta network that gave some arbitrary YZ, this YZ sort of parameters, which have no predefined meaning. So imagine your agent is predicting three things, which is pi, which is policy. Policy is just action probabilities of different actions, and y and z, which have no meaning at all. and there is a meta network, a target network that is generating these Y and Z targets for them. So instead of the target being like handcrafted by human, which is R plus gamma V of S prime, you have YZ, which is just being produced by a meta network with no semantic value at all. It's just some number, and your agent has to predict, these numbers that the meta network is producing, and the meta network is incentivized to produce YZ in a way that maximizes the reward of the agent. So it's very counterintuitive, but what it ends up doing, I'll spend some time because it was, a little bit complex to understand, but I think it will make sense by the time the slide is over. So as I said, you have the agent that interacts with the world, it generates a trajectory. The trajectory, based on the trajectory, instead of the agent trying to maximize or sort of trying to predict what the handcrafted TD learning sort of numbers come up, it predicts whatever the meta network is generating. And if you see, this is the meta network. What meta network does is that it takes a trajectory and simply generates this y hat and z hat for agent to sort of predict. And this is the agent. Agent gets observations, and it predicts a policy. It predicts y and z. And of course, there are additional heads that predict the value function and next policy prediction. These they show for stabilization, but the important bit was they predict y and z which have no semantic value. And if you see, the whole loop has this meta gradient where they're just trying to maximize reward over all internal loops. So yeah, very counterintuitive. Why should y and z do anything at all? But they show that once they do that, at least on Atari, they beat all the sort of standard state-of-the-art. Dreamer was state-of-the-art, but they beat it. And the amazing thing is that if they train on Atari, without any other training, the meta network ends up performing SOTA on other benchmarks. ProcGen is something that generates environments procedurally, so the network has never seen that. So they end up sort of outperforming on these, and they show a lot of out of distribution generalization of this meta network. So meta network is truly learning something about the RL process itself, which generalizes across RL environments. They also have a very nice section in the paper where they talk about what are these Y and Z really representing. Of course, they must be doing some work. That's where the whole alpha is coming. And if you can see this, these are different rows showing how these values change. This is the Y. Let's just interpret Y right now. They do some kind of entropy sort of calculation over Y, which shows how the Y is changing. And they show that across time, Y ends up predicting salient events like large rewards. So this is a large reward that's coming. The Y sort of the confidence sort of spikes up after that. And similarly, in terms of Atari, it ends up predicting when their policy is going to change. And they also do some analysis on where is Y paying attention to in frames. And they show that while traditional value network pays attention to what's just coming next, the Y ends up paying attention to more distant enemies. And in the ablation, they show that without these things, which is Y and Z, they perform really, really badly. So without prediction, they just don't perform at all. So they are very critical for performance of the network. I think the lesson from this really is to try to sort of just reflect on why human crafted algorithms have fallen short here. I think a couple of points here. One is, of course, human crafted algorithms are not context dependent, right? So when you write, let's say, an algorithm for TD learning, that will behave always in the same way. Of course, it's math, so no matter what, it will behave the same way. And same with PPO. PPO, if you're sort of doing, pi old into exponential of advantage, it'll always be that no matter what's the context. But in meta learning, you can have these very context dependent targets. And similarly, often we are sort of grappling with, how do we sort of trade off bias and variance in our RL. how much should you rely on bootstrap rewards versus how much should you have like an estimate of the value. But why not learn this trade-off automatically, which is very context dependent? And that is also what meta learning would be doing. And similarly, when we talk about averages, where the value function would predict the average of the state, but it sort of collapses all the richness that is there. Maybe 50% chance it'll be an amazing reward, 50% of chance it'll be like very bad for you, or maybe it's just a tail risk of extremely hard kind of a difficulty for you, and you always collapse that in the average. But a meta learned sort of policy would just be paying attention to all these nuances automatically, right? Because ultimately you are sort of incentivizing it to learn over so many data points and come up with these trade-offs automatically. And similarly, there is no uncertainty modeling. Update rule behaves the same all the time. And similarly, throughout your training, you have the same algorithm, but oftentimes early in the training you need something else, and later in the training you need something else. And I think a lot of RL papers, of course, are motivated by trying to very carefully design trade-offs. What do you pick? Because you'll have so many papers that try to do different things early in the training, later in the training. But now researchers are starting to learn all of these automatically because data collection has become very cheap using the GPUs. The last in taxonomy of meta RL, you can literally, again, previously you had the network, again, still very handcrafted, where you had Y and Z, etc. And you learnt what those Y and Z did. But the ultimate of it is just throw everything at an LLM and have the LLM do it. And this is, of course, what AlphaEvolve did last year. If you've not paid attention to what AlphaEvolve did, it's just very, very simple. As I said, you have like a piece of code. It can be any algorithm or a set of algorithms, and you mark different blocks on it. Let's say you say, this is the block, start and end, evolve, start and end, evolve. And then you have like a prompt to an LLM where you give what you need to do. You say that you're an expert RL engineer and you need to improve this. And then you give previous algorithms, previous code, their performance, and then the current one. And what LLM ends up doing is, suggesting what you should be trying in these blocks that you've defined. It's just as simple as that, where the loop is extremely simple, but the magic is in what it ends up doing, right? The AlphaEvolve ended up having SOTA on so many of these problems, which were, and this is SOTA over human best. So it is literally like new knowledge created in the world. That's how I look at it. And it was just not these theoretical, mathematical, pure mathematics problems. It had a lot of real world impact at Google also. At Google scale, saving 0.7% of global compute resources is a really huge deal. And they also got fastest matrix multiplication algorithm using this method. And if you see their ablations, this evolution is extremely important. So this method sort of really works. Another example of it by another group was where they discovered new algorithms for large language modeling, reinforcement learning. So if in LLMs you have algorithms like DPO, RLHF, where you're trying to have algorithms, or even GRPU, etc., where in the post-training phase you have algorithms do more of something and less of something else. Again, this seems so simple that it should not be even possible, where they just give a loss function, and the foundation model LLM proposes a new loss function, and they evaluate a new loss function, and they do this whole loop all over again by giving them outputs of how the previous suggestions ended up doing. And in that sort of process, they ended up sort of discovering this disco pop algorithm where the win rate was just much higher than the current state of the art, which I believe is DPO. Extremely simple, but worked very effectively. And the last example in this whole taxonomy of using LLMs to evolve algorithms is this paper called Eureka, where the whole point was how do you even design good reward functions. A big challenge in getting RL to work is doing reward function modeling. For example, if you want to build like a model of a hand that spins spins, let's say, pens, just like we'll do in our classes. Designing the reward function itself is so difficult. But what they did was they simply had like an environment with the hand. It's any environment which supports robotics. And then they gave LLM like a task to design a reward function to make the shadow hand spin the wheel, the target orientation. The LLM does that, you sample it, and you then use like a visual language model along with the trajectory of it, and you see how well did the reward function behave, and you go with this whole loop. So the LLM itself becomes reward function designer in that case. So I'm going to end my talk with some of the experiments that we're doing at LostFunk in this domain. The one is that we verified the speed up of these GPU environments ourselves, and this is what we got. Of course, Gymnasium is the old CPU-based environment, and Gymnax is the GPU-based environment, and it has, I think, 10x speed up right off the bat. But the magic is if you can do batching. So if you batch, you get like an insane amount of throughput, and this is, I think, 1 e raised to power 8, which is, I don't know, 10 million. So it's sort of like 10 million steps per second, and this is what allows you to do meta-RL, right? Our first attempt was using evolutionary search to invent new RL algorithms. So the loop was this: the baseline was optimized PPO code. What we instructed our LLM to do was to target genuinely new novel algorithms, and we evaluated those modifications on 3 Atari games, their average performance over multiple seeds, and then that became the fitness of the evolved algorithm, which is used for selecting the right parents to create like a child program. And we normalized all of them so that they were at the same scale. And what we did was we evolved for 1 million steps, and then we evaluated the best algorithm for next 9 million steps. What we found out was this, where in the initial 1 million steps, our evolved algorithm performed better or equivalent to the baseline PPU. But once we let it run, it sort of stagnated. This was likely the case of the evolution itself was overfitting the problem. But notice that it is the same algorithm that's working on 3 different environments. But we clearly saw that this was not going anywhere. If the evolved algorithm was genuinely better, this red line should have been above blue all the time and not sort of flatten up. To give you a taster of what the evolved algorithm did, what LLM did, it did some kind of changes. For example, in the PP algorithm, it added momentum-based learning, where you exponentially sort of weigh recent trajectory more. It would sort of also add some kind of entropy so that you could adjust exploration automatically, and it would have dual architecture, etc. And if you think about it, I think all of them are from literature. It didn't seem like it is doing here right now something genuinely new. I think it was sort of combining these things interestingly, but I could sort of trace back these changes to what people have already explored in the literature. We did tweak our algorithm. We did certain things, as in we started rewarding novelty, because we saw that LLMs end up sort of doing same things all over again. So in the reward we added, the more different the current solution is, the better it is. We terminated underperformance early. We experimented with sampling strategies. We tweaked fitness. So we did lots of things, and they improved a little bit. So you see that now we had performance for a while. Just to remind, we trained only till this part, 1 million steps. After this is all evaluation, but somewhat like a mixed bag. We couldn't really say we hit a home run. Why this didn't work? I think this didn't work because obviously RL algorithm is inherently complex. Like PPO is just not like assembly of multiple things. I mean, it could have been that if we had scaled even more, who knows, if we run it to infinity, we'll find something amazing. But we don't have infinity of compute, nobody has. But our current hypothesis is that this problem is, evolving algorithm is probably at right now a Google scale problem. I'm pretty sure the alpha evolved results we saw, it would have been an output of, I don't know, how much of compute that none of the labs here would be able to afford. But if you have limited compute, I think that problem is still relatively unsolved. because current human algorithms are optimized to a very good degree, and any intervention you make there is probably going to break them in some way which LLM doesn't recognize yet. And the second also, I think generalization across tasks is fundamentally hard. If you perform really well in one environment, it's very hard for the same set of hyperparameters algorithms to perform equally well in other environments as well. And that made us question, is that even important? Should we be even aiming for generalization across systems? Then we asked, what if we could keep the RL system intact but played with the environment itself? So instead of tweaking the algorithm, can we tweak the environment to have like a better performance? So right now, these are the experiments we're doing. We are evolving the MDP itself. So if you have a traditional MDP with action, reward, state, we instruct LLM to sort of just modify observation for a new observation, action to a new action, reward to a new action. So it's like a transformation, and this O prime, A prime, R prime is that goes into traditional PPO. So we're not touching the algorithm at all. We're just modifying the state space, the reward, and the actions using LLM. And we experimented on, Brax Ant, again a GPU-based environment. You can see what kind of changes LLM did. So in the observation space in Brax, you have these 26 observation. It ended up combining to more quote-unquote semantically interpretable things like linear velocity, angular velocity, joint velocity. So now the PPO algorithm has, fewer inputs to work with, and hopefully those inputs are more semantically intuitive. And action also we have no idea why it did this, but it simply multiplied by 0.86, which made all the actions just slower. It worked best, and this is the thing with the evolutionary algorithms, right? You don't know why something is working, but it did that. But I think the most of the interesting bit was when it did like reward modeling, where if you see that the modified reward had things from observations itself. So one of the interesting, I think that's one of the sort of alpha that's not exploited yet, that observations themselves could be rewards. With humans, we never get reward, right? We build our own rewards using the observations we see. And I think more and more we'll start seeing the observations or something in the state become transformed into the reward itself. So you can see that it gave height bonus so that, it encourages maintaining a specific target heights, forward bonus so that it strongly rewards forward velocity, and then penalty where it would penalize a latent movement, etc. And I think this time it started working, and we're very excited about that, where we trained it for again same 1 million steps, but if you run it to 10 million steps, it still has a statistically significant difference over the baseline PPO. And just to check whether this was like a fluke or this could be repeated, we tried it on another environment, humanoid, and now we had like even like a better sort of performance. And this time we actually sort of had the environment run for 50 million steps, and it worked really wonderfully. As a taster, what it did again very similar. By the way, in addition to evolving the MDP, we also evolved the network itself. So although not too many changes were made in the network, but you can see that it expanded the state space from 32 to 64, but reduces the number of layers. But the more interesting bit was in the rewards. Again, just like it did with Brax Ant, for humanoid also it sort of reshaped the rewards to something which is more amenable to faster learning. So promising results, but many open questions, and I think these are open questions for the field of meta learning itself. We need to do ablations on what's making a difference. Is it the reward evolution, observation evolution, or action evolution? We need to run this on more environments, and of course we need to run this on real world RL problems. Is it just that it works in toy environments, or does it deliver real world value also? And lastly, making it sample efficient. GPU is like a cheat code. You could generate like 1 million samples in a second, but how do we do this in the real world is the big question. So yeah, to conclude, I think this is like the take home message. Instead of doing X, we should probably start building systems that do X, and that's the whole spirit of going meta. Thank you.
Thank you for a wonderful talk. We have time for a few questions.
Thanks, Paras, for the talk. So you mentioned about this Y and Z in this meta RL, right? See, in reinforcement learning, typically this Y and Z will change from, let's say the standard expected, the RL that looks at maximizing the expected reward, or in the rest sensitive setting as well, the Y and Z will be different. So, do we have any interpretation of what these YZs mean and so on and so forth?
I think, as we saw on that slide, these YZs are just, I think one could do interpretability analysis on that, but it's probably just encoding things that the standard, my intuition is that it's just giving more things for the network to predict, which in theory should be able to derivable from the standard, TD learning formula, etc. But these are probably some non-linear kind of transformations on the trajectory. If you go back, what they do is that they have like a network predict this, and the network is incentivized to maximize the reward. So my intuition is that these things are some complex functions. Ultimately all the signal is coming from reward. So some complex sort of function of, let's say, how fast the reward is scaling, how it's decaying, is it like coming in cycles. So these implicitly end up encoding those kinds of things, and when the agent is tasked to predict those, it just has to build better representations, and that's why it's sort of working better.
And maybe one more question. See, when you were talking about this PPO modification and things like that, did you see that it was trying to combine, other ideas from other algorithms like, let's say, TD3 and so on and so forth, or was it, keeping the core idea of PPO intact and making some, incremental changes to that? Do you have some thoughts on that?
I do think it was trying to do that. Akshat, are you around? Yeah. Do you want to answer that?
You can just 1 minute.
Yeah, it was actually making changes. It was taking aspects from other algorithms, like it was adding like KL divergence to like try to find the difference between two certain values. And I saw generally it was trying to see stuff from other like popular RL algorithms and try to integrate those ideas rather than make like incremental changes. Because I made sure the novelty metric was existent, because or else like it would initially just try to make changes to PPO itself that were like kind of incremental and useless. And I think to combat that, I introduced a novelty metric that like made it make more interesting changes, I would say. So yeah.
Thank you.
I think this evolutionary algorithm, the trade-off is always about exploitation and exploration. The farther you go from what's expected to work, the more chances that you'll hit upon a jackpot, but the more chances it will not work at all. So as a research problem, sample efficient evolution is like an open problem right now.
See, when you talk about evolutionary algorithms, my guess is that you start off with some different variants of RL algorithms, and you see which RL algorithms are working, and then maybe you use the best algorithms, combine them, and generate some variants of those algorithms. I don't know if you're trying something like this, and if you see something like this in your experiments. Anyways, I would like to hear more about it.
Okay.
Thank you.
Awesome.
Yeah, one question.
Yeah.
In the slide where you talked about the reward being modified, I think for humanoid as well as for ant, I'm concerned whether that's a fair comparison and whether PPO was also run on the same modified environment with the modified reward. That's the first part. And second, I think there's more experimental questions, maybe Akshat can address them. But secondly is the problem where one set of hyperparameters does not scale to different environments for a particular algorithm. I don't know if you saw that for ant and humanoid, which were the two experiments you presented, or whether there were two separate algorithms that were running for both of the environments, which led to better performance.
So the baseline was the same PPO, and all we did was change what is the reward observations, and there's no new information being injected externally. So it is a fair comparison in that sense. And for every environment, there is a different kind of MDP evolution that happens. And I think our inspiration was really how human RL engineers would do it, where they would spend a lot of time on reward engineering so that the algorithm is able to work with them in the best fashion.
Yeah,
And
that
we
makes
just had
sense.
LLMs try to do what human engineers would do automatically. Yeah.
Thank you.
So traditional meta learning, the MAML type of algorithms, they do the gradient of gradient type of architectures. But in the meta RL architecture, you are sort of more doing the hyperparameter tuning based. So have you thought about anything about the gradient of gradient in the model itself rather than the architecture?
Yeah, so I think they do like meta gradient. So obviously you could do both things. You can propagate the gradients from the outer loop to the inner loop also. It depends on problem setup. Right now at our lab we are doing what I sort of showed, which is really using evolving algorithms themselves. And I think of course code is not differentiable. So you can't, that's why you use, I mean if you could differentiate with code, you would not need evolutionary algorithms. It would be like a much simpler problem. But the fact that code cannot be differentiated motivates the use of the evolutionary algorithms.
Okay. Second part, so in this you showed that the YZ that is being generated by the meta network, so it takes in as input the full trajectories itself, right, to create the targets?
Yeah, I think it's rollout of 20 steps, and then it sort of goes back in time and then generates, just like you would do with the bootstrapping, right? You'd add up rewards. So it's just doing the same. It just goes 20 steps in future, and using that information generate these targets for the agent at that particular step.
So is it sort of approximating multi-step TD type of algorithms?
Yeah, approximately, but of course it's not TD, it's just learning from the data what's appropriate to be done. So as I said, in my previous answer, it might be modeling how fast, how big the reward is about to come and not just the average reward. Will the reward cycle? Will you get a very large negative reward? And in that sense, it ends up sort of accommodating for more nuances about rewards, which would interact over a trajectory in a very non-linear, unintuitive sense. I don't think we have good intuition of what's happening, just like I think we don't know what Alpha Zero is doing when it beat the Grandmaster. Yeah.
Any other questions? I have one question for you.
Yeah.
So do you have any intuition of, so in the last part of your talk, you showed that initially the meta algorithm was not able to beat the baseline, but then you tweaked some other parameters, maybe related to environment. It started performing better. So what's the intuition of which parameters are you tweaking? Is there an intuition of which are the important factors there, and why would it not overfit, or if it's not performing well, why is it not performing well?
I think PPU, I mean, the way I think about it, PPU is just so many ways it can break. But in the reward space or the action space, observation space, there's just few things to intervene. So evolution would work in a more sample. I mean, my hunch is that if we had the evolution process kept on running, it would have created like an algorithm that would have worked better than PPU also. But it's just a matter of sample efficiency, like most things. And when we talk about reward shaping and observation shaping, I think just the amount of stuff you're dealing with is much narrower than the whole algorithm. So the LLM is able to, I think, do a much better job in a sample efficient way there.
Okay, yeah, thanks. Are there any other questions? Okay, so
awesome. Yeah, thank you so much.
Okay. Yeah, thanks for a wonderful talk. Let's thank the speaker. We have a...
Thank you so much.
Thank you. Oh, yeah. In August 21, he finished his PhD in EE and Computer Science at Syracuse University. Before that, he finished his BTech, MTech, so basically dual degree in electrical engineering from IIT Kanpur. His research interests include federated and collaborative learning, stochastic optimization, reinforcement learning, and differential privacy. Let's welcome Pranay. He'll be talking about natural policy gradient for average reward and non-stationary environments.
I like the final sessions of the day. You can see the resentment in everyone's eyes that this better be worth my time. Okay, so I'll be talking about non-stationary environments, something which Karthik also talked about in the previous talk. So they say imitation is the most sincere form of flattery. So following Professor Borkar from yesterday and Prashant from today, I also have a quote which I just added. So it says, any sufficiently advanced technology is indistinguishable from magic. And with what Professor Sridharan talked about today with histopathology, work with Professor Guhan, like I got the same feeling. But I also get that feeling with laser pointers. I have still not gotten used to them. Okay, so this was a joint work with my colleagues at CMU. Niharika is a fourth-year PhD student. Ishika was a master's student at CMU. She's, I think, a first-year PhD student at UIUC now. Guanan and Gauri are faculty members in the ECE department there. Gauri was also my postdoc advisor. So you have seen a lot of these applications already, but reinforcement learning is essentially sequential decision-making under uncertainty. So this might be in data centers or in self-driving cars, as Ronak talked about yesterday, or in financial trading, as Prashant talked about today, or in recommender systems in a number of applications. Karthik talked about it in the previous talk. But something which is universal across all these applications is that there is non-stationarity in the system. So for example, in financial trading, the kind of market forces you have change with time. Sometimes you have a bear market, sometimes you have a bull market. Similarly with recommender systems, the user preferences change depending on the time of the day, depending on seasons, etc. What we want to do is, we want to do well in a time-varying environment in the long run. So this is the high-level goal we have, and we want to formalize what do we mean by doing well, what do we mean by time-varying environment, and what do we mean by in the long run. Okay, so this is the outline of the talk. I'll begin with some background where I'll formalize the three underlying terms. Then I'll go to the algorithm I'll be mainly be focusing on, which is natural actor critic, and I'll extend that to a non-stationary setting, which will give us the NAC algorithm. And then I'll talk about the regret bounds for this algorithm. If there is time, I'll also talk about some proof sketch, and then I have some concluding remarks. So this is the canonical MDP slide for reinforcement learning. The environment consists of some state and action sets, and we have some transition probability matrix and some reward vectors. So the trajectory is given by this. At time t, you are in state st, you take some action at and transition to the next state while also receiving some reward rt. Okay? And the next state comes from this transition distribution. So P is a transition probability matrix, R is a reward vector. In stationary MDPs, what most people study, both these matrices and vectors are time invariant. In this talk, we'll be talking about non-stationary setting, where the transition matrix will also change with time and the reward vectors will also change with time. Okay? So how do we measure whether we are doing well or not? It depends on how we look at the rewards. So usually people talk about maximizing the cumulative discounted reward, which is given by this expression. You have seen this before also. Eta is some initial state distribution, while pi is the policy that the agent is following. In this talk, we'll be focusing on average reward. Again, you saw this earlier in the morning. But this is what we are concerned with. For large enough time horizon, the expected average reward, which we denote by JPi because it depends on the policy pi. This is what we are trying to maximize. And under ergodicity assumptions, this average reward can be written in this simple form, that it's the reward for some state S and action A, where the state comes from some stationary distribution and the actions come from the policy pi. And the stationary distribution, it is the stationary distribution induced by policy pi and the matrix of transition probabilities P. Okay? So why do we care about average rewards? It's because discounting often introduces a time preference that essentially you care more about immediate rewards compared to what happens in the future. That's not always the right thing to do. So this is a cartoon from the New Yorker from a few years ago. There is a corporate executive explaining that, yes, the planet got destroyed, but for a beautiful moment in time, we created a lot of value for shareholders. And looking at how AI companies are going these days, we might be very well in this future. Okay? So just prioritizing immediate reward is not always the right strategy. So average reward emphasizes steady state behavior in the long term. And it is the right notion when you expect the system to run forever or for a very large time horizon. So for example, in queuing systems, where they are interested in maximizing throughput or minimizing average latency over a long period of time. Or other examples are communication networks, recommendation systems with continuous users, etc. So when we are in average reward setting, instead of simple value functions, we have relative value functions. So this is the relative state value function. It looks very similar to what you are used to, but there is no discount factor, and you are subtracting the average reward. Okay? So how well a specific state is compared to the long-term average reward. And similarly, we have relative state action value functions, where we quantify that if you start in state S, take action A, and then let the trajectory run, then how well do you do compared to the average reward? Okay? So just like we have Bellman equations in the more familiar discounted setting, we have Bellman equations here also. The first one is quite familiar, and the second one just has this minus average reward factor. Okay? So you can do value-based methods, you can do policy-based method. In this talk, we will be talking about policy-based methods. So value function-based methods have certain limitations. They can diverge under function approximations under certain settings. Policy-based methods, more specifically policy gradient-based methods, something what Prashant also talked about, have this performance measure, which we will use the average reward as the performance measure, and you move in the direction of the gradient or an estimate of the gradient of this average reward. The advantages are that sometimes in some problems, policies are easier to approximate compared to value functions, and you can inject some prior knowledge you might have about the environment, about the setting, into your policy. So this is a quiz slide. So in policy-based methods, you can have actor-only methods or you can have actor-critic methods. Who recognizes this guy? I know there is one movie buff in the audience. Yeah, who knows, who is this? Okay, so then the next question, which movie is this from? Okay, Goodfellas. What is playing in the background in this scene? Okay. So you don't know something about movies. It's Sunshine of Your Love by Cream. Okay, so in actor-only methods, which you can apply naturally in continuous settings, the limitation is that your policy gradient might have a high variance, right? So we might work with actor-critic methods. Who are these guys? Right, this is Roger Ebert. Who is this? Yeah, this is Siskel. So these are Siskel and Ebert. They were very famous movie critics. They had a show called At the Movies in which they critiqued movies in the US. So you might work with actor-critic methods where a critic learns the value of the policy that is being played, and given some actor policy, it evaluates how good that policy is. And then the actor estimates the policy gradient using the value of the value function that the critic has estimated. So The policy gradient will be based on the value estimated by the critic, and then the critic will in turn evaluate the actor's policy. He has a 4-scale thing, so a little more signal. Okay, so summarizing the rationale for what we are doing and why we are doing it, critic-only methods like value function-based methods might diverge under certain conditions. Actor-only methods are more sample efficient, but they have high variance. So actor-critic methods sort of give you the best of both worlds. And then there are natural actor-critic methods which utilize some second-order information, and that's why they can guarantee global optimality as well. So Professor Shalab has this 2009 paper, which is quite popular, on natural actor-critic algorithms. We use that. I would highly encourage you to read it as well. So the problem statement is that we are interested in the infinite horizon setting. We want to maximize the average reward, and we want to do this when the environment is also changing over time. And the approach that we will use is going to be natural actor-critic kind of methods. Okay? So let's discuss natural actor-critic methods now. So given your, the objective is given by your average reward, then the actor updates its policy using this kind of an expression. So here, this is the gradient of your average reward with respect to the policy parameter, and this is the Fisher information matrix that you are inverting. So using policy gradient theorem, this is the expression you get for the average gradient of the average reward. Here you have the state action value function, and that is getting multiplied to the grad log pi, or the score function of the policy. And you are taking expectation over, again, something we have seen before, that the state comes from the stationary distribution that is induced by the policy and the transition probabilities, and the actions are given by the policy. Okay? And f pi theta, whatever you are inverting here, is the Fisher information matrix, which is given like this. So we are doing something more than gradient descent. This might remind you of Newton's method or quasi-Newton's method. This is second order kind of a method. Okay? With softmax parameterization, that if our policies are parameterized by some vector theta, and the policy in any given state is given by this, so this is a softmax function. Okay? Under this parameterization, this natural gradient step simplifies to this thing. Okay? So given your policy, oops, this should, so I should clarify. So given your policy at the current time instant, the policy at the next time instant is given by this expression. Okay? This denominator is just a normalization. So whatever the probability of the action at the current time at the current iteration, it gets amplified or reduced depending on the Q function of that state action pair, and then you have some normalization and you get the updated policy. So does this update remind you of anything? Something more specific? How about multiplicative weights update, right? So multiplicative weights update is exactly looks like this. The problem here so far is that we don't have the state action value functions, right? So we need to do something about it, and that's where the critic comes in. So it updates the Q value functions using TD learning. Okay? Again, you have seen this in the morning. Given your current estimate of the Q function in some state action pair, you take the reward in the state action pair, and you have this TD learning update. You subtract the average reward, right? So S prime, A prime are the states and actions after transition. So from state action pair S comma A, you go to S prime and then take action A prime. Okay? Now the problem is we don't know eta, right? It is an estimate of the average reward, but we don't know that. So we need to estimate that as well, and it's a similar update. It's a simple stochastic approximation update, which uses the reward for the current state action pair. Okay? So we have the actor update, which required knowledge of state action value function, which was done by the critic, which required average reward estimate, which is here. So collecting everything together, we get this algorithm where the average reward is updated, subsequently the critic updates the state action value function, and then the actor updates the policy. Okay? So this is our building block. The only limitation here is that the reward functions are not changing, the transition probabilities are not changing over time. In non-stationary environments, both might change. So that brings us to the non-stationary variant of this algorithm, which we proposed. So the idea is that if the critic can estimate the value function of the current policy, then the policy update is pretty straightforward. But if both are happening simultaneously, you can still make it work as long as the critic step size is much larger than the actor step size. So this is basically the 2 time scale stochastic approximation technique, that as long as the critic step size is much larger compared to the actor's step size, the critic can achieve a good enough estimate of your current policy, because the policy is changing much more slowly compared to the critic. But now the environment is changing, so that introduces a little more, a few more challenges. So instead of a fixed MDP at each time instant, where these P and R were fixed matrices and vectors, now we have time-varying environments where we assume the state and action pairs, the set of states and the set of actions is fixed, but the transition probabilities and the reward vectors can change with time. Okay? And then actor is chasing a moving target, right? So at each time instant, your optimal policy would be given by something like this. So this is the average reward for the policy at the current time instant, right? So if this is the environment at the current time instant and RT is the reward vector, then for if you maximize this thing over pi, you get the optimal policy, but only for the current time instant, right? So you are chasing a moving target in a time varying environment. And to make it more concrete, suppose you are interested in stock market prediction. The stock market evolves over time, right? So this is the data of how S&P 500 index performed over a very long period of time. You see these seasonal variations, right? But this is past data. Even if you know there would be seasonal variations, the seasonal variations for this year might be slightly different from how they were in the past, right? And you will have to evolve with them constantly. So you are chasing a moving target. A more familiar example would be in several Indian weddings, the groom's parents are the moving targets who keep on changing their demands. So you might be familiar with that. But again, we have a few challenges, like we need to explore more aggressively now than we did in the stationary setting, right? Also, the environment might change so much over a small period of time that the information we learned in the past is no longer useful. So we might need to forget some of the old information, and we will need to balance this forgetting with learning the new information, okay? So that brings us to the non-stationary version of natural actor critic. Essentially, we divide our entire time horizon capital T into several segments of length T over N. And then at the beginning of each segment, we restart the algorithm. So rather than running the same algorithm over the entire time horizon, we are running the algorithm over segments of the entire time horizon. And as soon as a segment ends, we restart the algorithm. So we ran a natural actor critic algorithm up from beginning to time T over N, then we restart, run the same algorithm again, at 2T over N, we restart again, and so on, right? So within each segment of length T over N, we are running essentially the natural actor critic, which we saw earlier. The only difference here, you might not recall the expressions, but the only difference here is now your reward functions are changing with time and your transition probabilities are changing with time. That necessitates the restart, okay? In this case, we assume step size is a constant. I'll get to that when we go to the regret bound. And they depend on how fast your environment changes, right? So let's look at the regret bounds. Let's first define what regret is. So recall that I said that we are interested in maximizing the time average long-term reward. In this case, our performance metric is slightly different. We are interested in something called the dynamic regret. And what that means is you look at the average reward of the optimal policy at any given time instant. So pi t star is the optimal policy at time instant t. You look at its average reward and then compare against the reward that you actually get when you run this algorithm, right? And you sum this over the entire time horizon. That gives us the dynamic regret because our actual reward is actually comparing against a time varying dynamic thing. So I've already said that. And this is much more challenging compared to static regret, where here what you compare against is a fixed thing which doesn't change with time. Okay? So this is what we will be working with. And we will try to essentially ensure that this quantity does not grow linearly with time. If on average, if you normalize it by t and it goes to 0 as t increases, then we have done on average as well as whatever the optimal thing is. Okay? So this thing should not grow linearly with time. That is our goal. Because it's a time varying environment, so we need to quantify how the environment changes. And this is given by these two quantities, which we call variation budgets. So how much the reward vectors change over time is quantified by this delta RT. So we sum whatever the cumulative change in the reward vector is from one time instant to the next. And similarly, we look at what is the cumulative change in the probability matrices from one time instant to the next. And that gives us the variation in how the environment changes. And I'll only talk about delta t, which is the summation of how the rewards change and how the probabilities change. We have separate dependence on both of these in the paper. And obviously, we don't know at a given time instant how much will the environment change or how much would the reward vector change to the next time instant. We don't know these individual quantities, but in what I present today, we know the summation somehow. Okay? And then at the very end, I'll just say one sentence about how do we relax this assumption. Okay? And we make this assumption about uniform ergodicity. So we assume that the Markov chains generated by implementing some policy pi, given some transition probabilities p, these are uniformly ergodic. What I mean by that is there exist two constants, some positive m and some rho which is strictly smaller than 1, which ensures that when you compare the distribution of your actual trajectory, starting from some state s, you look at this trajectory at some time instant tau in the future, and then you compare this distribution of your trajectory with the actual stationary distribution, which you would have got if you had run this policy, then this distance, this total variation distance, exponentially decays as you move further and further along the trajectory. So as you increase tau, as you roll out your trajectory, over time, the distance from the stationary distribution is exponentially decaying. Okay? And we assume, this is a strong assumption we are making of uniform ergodicity, that whatever policy you run and whatever environment you run in, there is always uniform ergodicity with some m and some rho which is strictly less than 1. Okay? Under this case, so this is the dynamic, this is the variation budget we have. If we use this choice of step sizes, so recall this is how the natural actor critic runs in each segment. We divide our entire time horizon into multiple segments, and within each segment, this is how natural actor critic runs. These are the choices of the step sizes for average reward, for the critic alpha, and for the actor. These depend on the knowledge of the variation budget. And this is, we also need this variation budget to decide how many times we will restart our algorithm, how many segments we will have over the entire horizon. And with this choice of step sizes, we get this bound on the dynamic regret. So for now, only focus on the last two terms. As you can see, we have a 5/6 dependence on capital T. So if you normalize it by capital T, this would go down as you run for a longer and longer time horizon. This is not, I can tell you upfront, this is not the best possible thing you can achieve, but this is sublinear. Okay, so as long as your delta T, your variation budget is sublinear in T, this entire thing is going to be sublinear in T. Okay. And we have some natural effects of non-stationarity. So as delta T, the variation budget increases, we get worse budget, we get worse regret, which is understandable. If we have a rapidly changing environment, meaning we have a large variation budget, in that case, naturally, the algorithm needs to adapt quickly. Therefore, we would need a larger step sizes. This is what this shows here. As delta T increases, you will use larger step sizes. Also, we'll need more restarts because the environment is changing quite a bit. And now you can also look at the dependence on state and action, the size of state space and action space. And naturally, for larger state space, action space, you will need more samples to detect that there is a change in the environment. So you will get a worse regret correspondingly. Okay. Yes.
So the high-level question is, when you're talking about the discounted versus average, you said that in average I care about the steady state, which is like long run. Initially, if I take bad actions, it should not matter. But your regret definition is saying that at every time t equals 1 to t, I need to choose something optimally. So it's not really steady state in that sense.
So if you look at the average, then if you have, like, let's say a few initial bad time instants, and if those time instants are like sublinear in T, then you can like get rid of that effect in the average regret, right?
Okay, so that's, and the second question I have is like, how do you don't know delta?
Yeah, so I won't go into that in the talk, but similar to how expert advice algorithms work, that you have multiple algorithms running and you divide your entire time horizon into, like if T is your time horizon, then you run log T algorithms in parallel with certain estimate of your variation budget, and one of them would be accurate, and that would help you get the best regret. It's the same idea. So it's the bandit over RL framework. We have borrowed from other papers to do that.
Yeah, I'm not familiar with this.
Yeah, any other questions? Yes.
From the MDP equation, you showed like the regret bound. From the state space, is it like seems to be discretized, like it's not continuous, just states and next.
Yeah, this is finite state space. Finite state space, finite action space. Yeah.
Okay. So so things will change if it's continuous state space action.
Yeah, we haven't looked in continuous space so far. Like this turned out to be challenging itself.
Yes,
yeah.
correct.
Yeah. So this is the simplest setting possible. So I gave a very similar talk at TIFR last week. Guhan was there, and one of the students at the end says, "This looks so simple. Like, what was challenging in that?" Yeah. So it's a very simplified setting we are working with.
So here, I guess how delta t is distributed according to time, that doesn't show up, right? So can we see that somehow? Like right now, you divided your epochs to be uniformly spaced.
Yeah, so that's a great question. It turns out that, so I'll talk about a lower bound towards the end. If you have abruptly changing environments, those are much harder compared to slowly time varying environments. So we can improve this regret bound if you have some very small constant change at each time instant. Then we get a better bound than this. But in the worst case, with abrupt changes once in a while. This is the, so actually the lower bound also, this is how they construct that for a small window you have one environment, in the next window you will have a very different environment. So you have these discrete significant changes in time. That turns out to be a hard instance.
Thanks.
Yeah. Okay, then
One question is, so do you assume that the Markov chain ultimately settles into a stationary distribution at all, or it's just non-stationary forever?
no, we don't assume it settles. Yeah, like this at all time instants, it's a different environment.
I see.
Yeah. So it has certain better convergence. Oh, sorry. Yeah, so the question is why natural policy gradient? So it had a few better convergence results in the model-based setting. So that's why we thought of doing natural actor critic. But you're right, like you could potentially go to, like we did not analyze actor critic in the non-stationary setting. I don't know if people have done that so far. Yeah. Yeah, we didn't. We didn't do it. Yeah. So like these are all open questions for you. Like I don't think people have analyzed non-stationarity in the actor critic setting. In the value function based setting, I'll talk about that paper towards the end. There is a famous paper which has done that, but in actor critic, I don't think so. The lower bound is t to the 2 by 3. Yeah. So it's, so initially we had 6/7, and then after a lot of work we were able to improve to 5/6, but yeah. Yeah, they do. So it's delta t to the 1 by 3 and t to the 2 by 3, the lower bound. I mean, like they will sum to 1, so yeah. And the lower bound is, okay, so foreshadowing, but the lower bound is also better than the dependence on state and action sizes. Yeah, I'll get to that towards the end. Okay, so next would be a slightly heavy part of the talk. Yeah, so I have a proof sketch. I'll do some amount of it and then I'll skip the rest. So this is the dynamic regret that we are trying to show that it is sublinear. Just to remind you, the optimal policy at time t is pi t star, and you look at the average reward for that optimal policy and compare it against the actual reward that you get at that time instant. Okay. So we begin by just splitting this into two terms. We add and subtract jt pi t. So if you look at the first term, let's call it I1. This is at time t, if you run the optimal policy, this is the average reward you would get. And at time t, if you ran the actual policy pi t, but somehow knew the stationary distribution, then this is the average reward you would get. Okay? So this is how much the average reward compares for the optimal versus the actual policy. And then because you have added jt pi t, so this is how different the average reward of your actual policy is compared to the instantaneous reward. Okay? So we'll try to bound both of these separately. Let's start with the first one. I've already said that. Yeah. So if we look at the first term, again we add and subtract a bunch of things. So first I write this summation, which doesn't specify the different segments we have divided the horizon into more explicitly. There are n segments of, let's say, length h each. And then we add and subtract a bunch of terms. So this is the first term. So basically you can think of small n capital H plus small h corresponds to t. Okay? And then we add and subtract a bunch of terms. Let's look at each of them separately. So the first term, this is again the optimal average reward for the optimal policy. And then we are comparing optimal average reward for the optimal policy, but at a different time instant. So this is some random time instant in a specific segment, while this is what happens at the beginning of the of this segment. Okay? We have added this thing here. Now, this is what happens at the beginning of the segment, and this is at the beginning of the segment. If you ran the policy, which you actually ran sometime into the future, then what would have been the difference? So the first term is essentially difference in optimal average reward at two different time instants. The second thing is how different is some policy at a given time instant compared to the optimal average reward at that time instant. Okay? And the third thing is, now we have the same policy but two different time instants. Okay? So how would this policy do in two different environments? Okay? So we are dividing our this simple difference into these three terms. Now intuitively, this I3, because this is just difference in optimal average reward in a single time instant. This should depend on how much the environment changes in a segment, right? Similarly, I5, again, you are looking at the same policy at two different time instants. This should also depend on how much your environment changes, okay? And then the third, the middle term, the I4. So this depends on how suboptimal the policy that you used at some time instant, how suboptimal this policy is, okay? This depends on our algorithm. So this should require a little more work. And N, we'll have to choose to balance exploration for change versus exploiting good policy in the, like learning a good policy, okay? So the first and third, as I said, they should depend on how much the environment changes. These turn out to be fairly easy to bound. So the first thing, how much does the optimal reward change within the same time instant, within the same segment at two different time instants? This you can bound in terms of how much the reward functions change and how much the environment probability transition matrices change. Similarly, this thing, like how well does this policy do at two different time instants? This should depend on the policy as well, but using some crude bounds, which like don't matter at the end, you can again bound this in terms of how much does the reward function change and how much does the transition probabilities change. So far so good. These are basically bounded in terms of how much your environment is changing. The third term, the middle term turns out to be more challenging because this will depend on your algorithm, like how suboptimal your policy is. So we can use performance difference lemma for the average reward setting, and it's given by this thing. So if at the same time instant, you look at how well two separate policies do, pi and pi prime, at the same time instant, then you can write it like this. So like, I always forget this. So the rule of thumb is that the state and action pair come from the stationary distribution and the policy of the first term. So the policy in the first term, d pi and pi. And the advantage is computed for the second policy. Okay? So you are running things in the Markov chain induced by some policy pi, but you are looking at advantage of the other policy. Oops. Yeah. And then you can look at this difference, how suboptimal your policy is. You can bound it in terms of this advantage, and I'll just write this term here, this advantage here, and essentially you can bound it in terms of the error of the critic and how much does the environment change. Okay? So the change in the environment we have seen before, this is easy. How the critic changes, this now turns out to be the challenging part. Okay? So now we need to look at the critic update. So far we have only looked at the actor update. Now we need to go to the critic update. Okay, so there are a number of terms in the critic update. So what I can tell you is So remember, this is the critic update, and if you essentially look at the error in the critic, so this is your actual value function estimate of the critic, and this is what you should actually, what the critic should actually get. So pi t is your policy, qt pi t is the actual value function for this policy. If you look at this error, you get some contraction, right? And then there are a bunch of other terms. One of them depends on the average reward error. So critic update requires estimate of the average reward. This is understandable, right? Then there is drift in the value function. Again, you can imagine this should depend on how the environment is changing. There is some higher order terms, and there is some error due to Markov noise. Okay? Right. So essentially, all these terms in the critic error, you can bound them. The drift in value function, as I said, would depend on how the environment changes and how the policy changes. Okay. So this is getting a little convoluted, but okay, this is the last slide I'll talk about in the proof sketch. But essentially, your actor error depends on the critic error depends on the average reward error, and then there is a coupling between the average reward error and the critic error. And then you need to do something to control this Markov noise. Yes? Yeah. Yeah, so as I said, if there is small change at each time instant, we get a better bound. So at each time instant, if you bound this thing and this thing, summation of these two at each. Okay, so let's say this is bounded by epsilon at each time instant, and this is bounded by delta at each time instant. The bounds simplify significantly. Algorithm is like straightforward. Yeah. Okay. I think so. Yeah. Yeah. Gamma and alpha. Yeah, they are the same. Okay, this is the average reward, and as I said, it depends on. No. Something, okay, I'll skip this thing. This is too much details. So just to summarize, like this was, I had split the dynamic regret into two terms, and I was talking only about the I1 term. You can similarly bound I2 term. And so I1, the first term, you can bound in terms of change in the environment, error of the critic. Then error of the critic, you can bound in terms of change in the environment, change in the policy, error in the average reward, and Markov mixing because of ergodicity. Then this thing you can similarly bound in terms of how much the environment changes, how much the policy changes, Markov mixing. And this I2 term, you can bound in terms of change in the environment and Markov mixing. Okay, I know this was heavy, so that was it. Okay, so now this is the lower bound. It turns out that for any learning algorithm, there exists, they constructed an MDP such that the dynamic regret is given by this lower bound. And here D is the diameter of the MDP. So they have better dependence on the state, the size of the state space, the size of the action space, as well as the time horizon. Okay, so this is the lower bound that they had. So why the gap between the lower bounds? The gap arises because the bound that we use for stationary natural actor critic, like it turns out that is a loose bound. So we have to use a single loop algorithm with a 2-time scale analysis for natural actor critic. Single loop is fine, that is necessary because it's a constantly changing environment, so you cannot run a double loop algorithm. But it turns out the 2-time scale analysis of natural actor critic, this leads to worse regret even in the stationary setting. So it leads to t to the 3/4 regret, and the lower bound we saw is t to the 2/3. So definitely this cannot work, but our analysis forces us to use a 2-time scale method. Yeah, so for a 2-time scale natural actor critic in the infinite horizon setting, this is what you get in the stationary setting. So definitely this is not the right tool to use, right? So this 3/4 then gets amplified to 5/6 when you look at the entire horizon. Okay, so you need something better. Potential next steps, so matching the lower bound, like we would love to do that. There is a Q-learning based algorithm which matches the lower bound. It's in the same paper. They propose that algorithm. Constraint setting, so this ties back to, this ties back to what Ronak, where is Ronak? What Ronak talked about yesterday. So if you are, for example, in the autonomous driving setting, you would have certain constraints as well. So along with regret, you would also need to worry about the constraint violation, right? So the simplest thing is you want sublinear regret and sublinear constraint violation. But especially in autonomous driving, you don't just want sublinear constraint violation, because if a car does something horrible at a single time instant and then behaves well for the rest of the horizon, that's not really a good thing, right? So we need certain stronger notions of constraint violations in that case. So this thing has been studied under a very simplified like OCO, online convex optimization setting. TIF folks, Rahul Vaze and Abhishek Sinha have worked on this, but only in the OCO setting. Also, we assumed that the environment is changing somehow. We don't know and we don't care. So these changes were exogenous, but can we say more if the changes are caused by us, if the changes are endogenous, or if the changes are caused by our actions? For example, in self-driving cars, how you are driving would impact what you see next, right? So you are actively causing changes in the environment, right? Similarly, in recommendation systems, the rewards might be endogenous. For example, once a specific product is recommended to you for the first time, right, the reward is higher. But if you keep getting recommended the same thing, for example, on YouTube, if you keep getting recommended the same thing, then the reward is going to be decaying, right? So endogenous reward, how, like, can we say something more in these settings? This is again open. Also, like, very importantly, how do these methods perform well in practice? Like, I only said that the regret is sublinear. Like, what does that mean in practice under different applications? Again, all these questions are open. So to summarize, we discussed in the model-free setting, we discussed a policy-based algorithm, more specifically a natural actor-critic-based algorithm in the infinite horizon average reward setting. This was essentially natural actor-critic with restarts. We proposed a bad but the first dynamic regret bound in this setting. There is gap between the known lower bound and what we have achieved. There was a question, what if we don't know this variation budget delta t? So we have an algorithm which adapts to the knowledge of the variation budget. If you want function approximation, we have results for linear function approximations as well. So this is the paper. So this got accepted to TMLR 3 days ago. So TMLR is the happy home for a lot of hated papers in ML community. So we are glad to have it accepted in TMLR. Finally, if I can have a few minutes for some shameless self-promotion. So I'm from C-Minds. It's the Center for Machine Intelligence and Data Science at IIT Bombay. It started as an interdisciplinary center where folks who did machine learning in different departments came together. And then we started hiring our own faculty. So Parth Pandit was the first faculty, and then the remaining 3 of us joined last year within a few weeks of each other. So these 3 are the core faculty. In addition, we have several, like, I don't know the exact number, but we have a lot of associate faculty from 15 departments, and we are actively hiring. So there are 4 of us currently. We have 2 more people joining soon. Someone is going to join in March or April, who is an oceanographer. Then we have another fellow joining late this year, and we have made out a few more offers. So we are rapidly growing. We have several graduate students. Again, this is number from last year, so this might have changed. We have admissions in March, April, so if you are interested, look out. We offer PhD programs, MS by research. We have an excellent pre-doc program, so if you are an undergrad student who wants to do some cool AI/ML work, so we have an excellent pre-doc program. And for industry professionals, we have an EPG diploma in data science and AI. And I want to mention this thing. So Parth won a very exclusive award I think late 2024 or early 2025. So this is something called AI 2050 Early Career Fellowship from Schmidt Sciences. So I think all over the world, only 15 people got this. This is quite exclusive, and Parth won this. So yeah, we would love to have few of you at Bombay. Thanks.
Thanks, Pranay, for an excellent and engaging talk. We have time for a few questions.
I mean, this is a general question in the sense you are asking for bounds on how much the transition probabilities and rewards may vary, but these bounds may be arbitrary or from actually what happens. So if you are given a setup where you know the environment is nearly stationary and maybe only one or two time instance it changes, in your algorithm, you're not doing anything to infer any of that. You're just using the bound, and the bound can be like too conservative.
Right. So these are very bad bounds so far. So as I said, if your environment is changing by a lot at a few time instants, those are really the hard instances where I don't think you can do. Like even in the lower bound, that is how they constructed the lower bound. So those are really hard. So even if at a single time instant, essentially if all the delta t is consumed at that single time instant, then like...
No, I'm talking about the reverse situation where the environment is nearly stationary. You just don't know how much it can vary. Maybe I put these delta t's on the higher side, but maybe the stock market doesn't evolve that much.
Right. Okay.
Doesn't vary that much. And because I put all these conservative bounds, I regret a lot. So I'm looking at the happy scenario with the unhappy bound.
Right. Yeah. So in online learning, there is this framework from, I think, 2022 called stochastically extended adversarial setting, where they are like, if the environment is truly adversarial, I should be able to guarantee a specific bound. But if the environment is stochastic and it's not changing, then I should be able to do significantly better. I don't know if that has been done in RL. But in online learning, that has started to be, it's being explored.
Yeah, but my question is like, at no point the algorithm tries to infer how much the variation is.
Right.
It just uses these bounds.
Right. So this was a conversation I had with Professor Veeravalli from IISc when he was there. So again, I admit this is a very bare bones algorithm. If you try to actively look for change, for example, change point using something like change point detection,
Yes,
that might do something significantly better. We haven't got into it yet. Yeah. I would love to explore that. Yeah.
Okay, thanks.
Any other questions? In the meantime, maybe I can ask a question. So, just a second. So first of all, so if you don't know the variational budget, do you need to know anything about it, or can you not show an impossibility result that you cannot perform sublinear, cannot have sublinear regret in that case?
So if the variation budget is linear, then the lower bound shows that you do get linear regret.
So when you don't know the variational budget, you're still assuming it's sublinear. Or, okay, I guess your upper bounds will then
upper
show
bounds
that
would be linear. Yeah.
linear. Also, did you consider like some sliding window kind of algorithms? Because considering fixed batch size or fixed epoch size looks a little lossy.
So, right. So when we have to adapt to the variation budget, then, even in that case, the window length is the same. Yeah, so the paper which had the lower bound, I think they considered a sliding window based algorithm, but we studied a very basic setting, like it's a fixed window length. Yeah, the only thing that was varying was that we had log T experts, and each expert had a different estimate of the variation budget. So like someone would have that the variation budget is between delta T by T by 2 to T. Another would have from T by 4 to T by 2 and so on. So you have log T such experts running the algorithm, and one of them would be right, that it would lie in that interval.
Thanks. Any other questions? If not, let's thank Pranay again.
Thank you. I really appreciate the invitation. I had one more question that no, but I could have used some other De Niro movie. Yeah, why Goodfellas? Because Goodfellas was one of the top 10 movies of Roger Ebert from the 90s. His top 10 favorite movies.
Okay, maybe I'll just. So thanks everyone for attending the second session of day 3. So we will have only one session tomorrow, but the session will start at 9 a.m. again. Okay, so I had a brief look at the feedback. Some of you are saying 9